determine the ion refraction. No, the ion excitation.
Yeah, but how it's mechanically used is to correct the you don't know the knowledge of the single frequency, what the band radius is, refraction, and therefore
General purpose civilian radios don't use it at all.
no, the GPS requires it to correct their error in range because it's assuming that pseudo range is a straight line. You've got to have the two frequencies to know there's different refraction.
But that isn't enough to affect the civilian use of GPS.
Right, so you don't normally get, well, they turned L2 back on, and they left it on. So that's how you're getting the...
But civilian receivers don't use that information. That's used by the DOD or another civilian, I mean, but that's used by the DOD.
Right,
or other
the Air Force stuff.
Because they need to know what the density, the electron density is of that cloud at various points of the cloud.
They don't care. They care about the refraction difference so they can correct the pseudo range. They care that I have to have two frequencies with the same cloud, and they know the refraction.
They need that information so there has nothing to do with experience.
Okay, well, then that's separate. Okay, they also use
But
it.
that's why it's there.
They also use it for GPS.
Is there any way to tap into your audio?
Not from the
The
civilian.
audio that you're adding to the streaming.
When you're trying to drop something down inside the window, yes.
So,
Where's Lynn off to on? You do what?
Okay.
so
I don't know the second thing you're talking about.
I'm saying, what I'm saying is there exists.
I have a license that you got taxed as well.
one thing that was
But the museum just reconfigured and what came out. We had Dean's Road, we had everything, but we got to get a lot of data. Well, long story, they're basically reconfiguring, building rebranding.
And then there's a portion of differential path.
We're gonna.
And the club, museum club down in Miami.
Chip, it's a Cerverico. I cannot read that. I didn't bring my flashlight. Darn it. Flashlight?
Give me my phone to use. My phone appears to have just quit.
Yes, I need a flashlight because this other guy trying to help, his ears are bad. My eyes are bad, so I can't.
What do you need to see?
Well, I want to see which one of these jacks is the input and the output.
I can just look at it for you. Yeah.
The difference.
You mean as far as the little USB thing, or no, the mic jack? This is aux out over here. This says mic over here.
Mic in?
Well,
Box is in the back.
No, there must be a speaker.
looks like mic right there and out over there.
Oh,
The second
yeah,
one.
this one.
That one?
You can plug here. Try it. Just try it.
Well, that's the headphone jack.
Yes.
You want to take audio out? Is that what
Yes.
he? Okay.
That's
Sorry, I thought he wanted to put audio in.
No. Ouch.
Okay.
In it's the microphone.
Yes, that's right. And you've got another microphone plugged in over here right now, right?
I know, that's not the microphone.
Oh, what is
this is the power supply.
Aha, so he
that's
needs to
power.
get the microphone.
Well, this one has a very sensitive, so you have problem with hearing? Okay. So if you want to listen better, I hope you can connect to this.
Oh yeah, for something like this, always better to have a mic by the presenter.
Or we can come on the front row. Go to the front.
You want it as close as you can. Yeah.
Okay, let's try that.
Okay.
And I think there are settings to control the volume to be. Can you hear?
Yes, I can.
Okay.
It's echoey, but I can hear. Okay, let me go rig up my rig.
That's not going to work.
No, how many cables can you string together? I'm going to leave this. Okay, this is it. Well, the gentleman that sits here that he's hard of hearing, so, but the problem is because it's white, you can't have wireless here. So I'm going to leave this like this and hope that he comes in soon.
You've got it, you're looking at something here. It penetrates the dome right there. You come down here, find the plane. These are the phase shifts you need to get there. As long as the radius is low.
Every year we have them on here.
Let's see, is there anybody else out there? for nominations, but I thought I would show you, this was in our last journal, of the people that were on the list for offices. So what I wanted to do, I believe it's also required as part of the bylaws that we have to open the floor and then we close nominations and then we go to tomorrow. Yes, tomorrow. So I'll ask the question, does anybody have the offices that are up? We have secretary, treasurer, those are the two officers, and then we have, of course, always 2 directors and 2 directors at large. And everybody understands the difference between a director and a director at large. Of course. Of course not. Directors come to meetings and participate because they have access. Directors at large, and correct me, Father, if I'm wrong, but directors at large don't have to come to every conference. So it's people that want to participate but have a harder time getting physically to our venue. Is that email? That's correct. Okay. So I'm writing that down.
Is there anybody that I could nominate for secretary?
No. But seriously.
By acclamation.
How about Ray Hartman?
Yeah, we could add. Where did it go? There he is. You got to understand. Cataract surgery and so you, but then I'm male, so anybody like to second that?
I second it.
Okay. So we will add you to the ballot tomorrow, and that'll be, we will. Ed Hartman.
You an officer?
I'm a writing officer.
Get a better marker.
Yeah, I know.
The black one works.
Improve their funding.
Everybody thinks they're gonna come back around.
Yeah.
They don't take it seriously.
Next time you say something to me, something more.
Okay.
No, you.
Any others? Anybody? Was everybody's tube steak made to order today?
Oh, yes, lovely.
Was that not the USDA?
Don't talk about what was in it.
Actually, that was, the chili was actually not too bad.
Yeah.
It was pretty good for.
And I haven't had a hot dog that big around for a
Was it
while.
Cal?
I mean, they were huge.
Any others? Anybody? Because I will close the floor for nominations. Do I have to ask somebody to, or does somebody make a motion? I think so.
I make a motion that we close.
I'll second. So the nominations are closed. So we have one that will be added, that's Hartman. And other than that, we have the ballots with us. I believe that I'll get them printed tomorrow. But it's in the. So, any questions? The reason I say that is our keynote is getting ready. I saw him testing. Thank you, sir. Always a plus.
See if anybody wants to count the votes.
Oh, I'm sorry. I need one volunteer to help with counting the votes tomorrow. Within and members of this. Raise your hand sometime. So we have 3 people that we're going to sequester once we get the votes, and then we'll count the votes for us.
Oh, you didn't talk about sequestration.
10 minutes. 10. I promise. So, without any further ado, where's Chip? You can take that off. And put this up here.
You should know, Ken, it was page 21 on 76, if you want to print that on and edit it.
Well, what I'm saying is that usually we print that blank balance, and I kind of like West Appleton still. I don't know who's responsible for it, but probably me. But I'll work on this. Hey, yeah, it's in the 30th. That's what that was.
Okay, thanks, Ken. Today, I'm very pleased to announce our keynote speaker for the 2017 conference, Professor Dale Gary from the New Jersey Institute of Technology. Professor Gary is a distinguished professor of physics at the New Jersey Institute of Technology, the Center for Solar Terrestrial Research. He's also director of both solar observatories in California. Is that right?
Well, I'm director of solar observatories, and then we have a director of the actual Big Bear Observatory that I'm sort of developed.
Okay. So you're director of two solar observatories, the Big Bear Solar, the Optical Observatory, and then the Radio Observatory in Owens Valley. We had our conference here, what, 2014? You're also a project scientist on a project called the Frequency Agile Solar Radio Telescope. Is that also at Owens Valley? Or?
That is only a gleam in our eye.
Oh, okay.
It doesn't.
It's kind of like our CubeSat. Yeah, NJIT operates these two observatories in California. Professor Gary, I believe that you're probably a world-renowned expert in solar radio astronomy. So thank you.
Okay, thank you. Is there a pointer, by the way? Thank you. I'm really happy to be here. I think I'm really learning about what this organization is about. I'm pretty awed at the range of things that you're interested in and that you're looking at. So I hope I can give you a little bit of an insight onto the what the sun looks like. And when I was thinking about this, you know, the sun looks like many things depending on what frequency you're looking at, right? So I decided that to do it justice, I should really cover the entire spectral range that we call radio that we can observe the sun in. And but at the same time, I realized that this 7 decades of frequency that we can call radio frequencies, from about 20 kilohertz up to hundreds of gigahertz, that's 7 decades of frequency, but it's also been about 7 decades of time since the sun was recognized to be a radio source. So I thought I'd try to put those things together and talk about observing the sun over 7 decades of frequency and time, both senses of the word. This is a photograph of some of the antennas of the radio array that I operate at Owens Valley Radio Observatory. There's actually 7 antennas in this diagram. You may count 1, 2, 3, 4, 5, 6, but that little dot in the background there is also one. So this is an array of about 1.5 kilometer maximum baseline, 13 antennas only. Fairly small antennas. These are about 2.1 meters across, but they're small on purpose because we want to have our field of view large enough to cover the sun. So at 18 gigahertz, our highest frequency, that 2.1 meters just matches the size of the sun. And we, of course, don't need a lot of collecting area because the sun is a nice bright source. So these 2.1 meter diameter antennas are just about perfect for our frequency range, which is nominally 1 gigahertz up to 18 gigahertz. So we're actually covering less than 2 decades of the 7 decades I'm going to be talking about. But over the years, I've looked at other, been involved with other ranges of frequency, so I'll describe some of my personal contributions there. So I'm going to give an overview of the sun and solar activity, just a couple of slides to orient you some of the things I'll talk about. And then I'm going to introduce 3 characteristic frequencies, because this 7 decades of frequency is really way too much to cover without some kind of framework in which to understand all the phenomena there. And I think these 3 characteristic frequencies of a plasma turn out to be ideal for that. And then I'll go through the 7 decades in frequency and in history, and then I'll just end with a couple of conclusions. So, first of all, the sun, I mean, many of you are quite familiar with what's going on here. I won't talk about the interior. The interior is, of course, not accessible to radio observations directly. We can learn about its structure from helioseismology, which is the study of acoustic pressure waves seen on the surface. And in fact, I'll show you some radio observations of those waves. So you can see those oscillations in the radio, but and those tell you something about the interior. But for the most part, I'm going to be talking about the exterior, what we call the atmosphere of the sun. So we have the photosphere, which is where sunspots reside. And in white light or ordinary light, you can see those sunspots as dark features on the sun. They are, of course, regions of very high magnetic field. And the reason they're dark is because they're suppressing some of the heat flow into that region, because the magnetic field is makes a good insulator for charged particles. They can't get into there so easily. But sunspots are not that dark. Actually, they're quite hot. They're around 4,500 to 5,000 Kelvin. The surface is about 6,000 Kelvin. So the sunspots are only relatively dark compared to the surface. But again, very strong magnetic fields. As you go up away from the surface, you come to the chromosphere, which is a region of around 20,000 Kelvin, 10 to 20,000 Kelvin temperature. And that's where most of the spectral lines in the optical are formed. A lot of features that you can see. You can see filaments, these dark regions here. You'll see coronal poles, regions that are a little darker than elsewhere. And then above the chromosphere, you come to the corona. And the corona is extremely hot, millions of degrees in temperature. And this is kind of a quadrant of what the corona looks like from an extreme ultraviolet image, which is sensitive to those very high temperatures. If you also see prominences, these are actually relatively cool clouds of hydrogen gas that are suspended above the surface, and they can erupt. And along with those can be coronal mass ejections. There's no coronal mass ejection shown on this slide, but I'll be showing you some in a moment. So the temperature falls steadily from the core to the surface, the photosphere, and that's a little bit above the photosphere is the temperature minimum. And that temperature is around 4,500 Kelvin. And then as you go higher in the atmosphere, rather inexplicably, the temperature rises again, and it reaches millions of degrees in the corona. So one of the important questions in solar physics, and actually stellar physics as well, is how these hot coronae form, and what is powering, what is the energy input mechanism, and how does the energy stay there? I mean, we can understand a lot of energy is going away from the sun, but it has to stop in the corona. If it just passes through, it won't heat the corona, so we somehow need to heat the corona. Solar activity involves these strong magnetic fields concentrated in sunspots, and those are storing magnetic energy. You can see them as loops in the corona, so they're guiding the charged particles and the hot charged particles in the corona. But these magnetic fields are storing energy, and they twist and get more complicated, and then they will be the site of sudden release of energy. And that sudden release of energy can power solar flares, various kinds of eruptions, and coronal mass ejections, which we abbreviate as CME. I'm sure many of you have heard that term. So the sun is extremely dynamic, and that's why it's so fascinating to study. So I'm just going to give you some of the time scales on which the dynamics occur. So we have sunspots that come and go on approximately 11-year cycle. Not an individual sunspot comes and goes on a much shorter time, but the overall activity period has about an 11-year cycle. If you count the switching of polarities from north to south polarity, it's actually a 22-year cycle, because each half cycle, each 11 years, it flips, and then the next cycle it flips again. The sun in addition to this long period, of course, it rotates every 28 days. And so sunspot regions can appear either by emerging from below, where they're born, so they're born underneath and they rise up and appear on the surface, or they can just rotate over the eastern limb as the sun is rotating. And of course, they disappear by dissipating, so their energy, as they release energy and form these flares and coronal mass ejections, etc., they're losing energy and they will simplify and eventually dissipate. Or they can just simply rotate over the western limb. So they can come and go in those two ways. They may actually, when they disappear over the western limb, survive the disk passage behind and then come back around and still be there on occasion. But during their 2 weeks on the Earth-facing side, we can see continued emergence and growth. So they can be born on the visible side and grow over time. Typically, it takes about 2 days or so for that active region to grow relatively rapidly. And from then on, they're various vigorous producers of flares, certainly large ones, and those flares are very, very sudden, within seconds. But they can also, of course, release these magnetic bubbles called CME, and this is a very poor rendition. Artists, what can you say? Doesn't look too much like a coronal mass ejection. The idea is that you've got some kind of bubble of plasma that is coming away from the sun, from the flare site. And those CMEs can drive shock waves. And the shock waves are typically thousands of kilometers per second. That's 2 million miles per hour. And they can also, those shock waves can accelerate particles. The flares themselves accelerate particles. And those particles arrive at Earth after maybe a few hours. So they're very fast moving. But the CME bubble takes perhaps 1 or 2 days. A fast one would be around a day, but typically about 2 days. And then when they arrive, those magnetic bubbles collide with Earth's magnetosphere, which again is a magnetic distribution, and then those two can collide and cause other activity, including northern lights, so-called geomagnetic storms. So the sun is very much of interest to us because of these geomagnetic storms, because of the effects of solar flares, because of the effects of these high-energy particles that can affect us, certainly assets in space, but also even high-flying aircraft and people on those. So let me talk about, in order to organize this 7 decades of frequency, I want to talk about these 3 characteristic frequencies. Most of you are probably well aware of at least 2 of them. So again, we're going to be covering from 30 kilohertz to 300 gigahertz, roughly. And we're going to need a simplifying principle. And this diagram is supposed to be that, but many of you will say that doesn't look very simple. But we'll see this many, many times during the talk, so hopefully it'll become a little bit familiar by the end. So to appreciate what I mean by this large range of 7 decades, the next 7 decades of frequency encompass terahertz, infrared, visible light, ultraviolet, extreme ultraviolet, soft X-rays. You know, the phenomena are changing so much that we need different names for them, right? The same is true of the radio spectrum, and in fact, I can divide those into these 7 decades with names, and I'll go through those in a moment. But the simplifying principles involve 3 characteristic frequencies, which I'm going to call f sub p, f sub tau equals 1, and f sub p. So the first one, f sub p, that's the electron plasma frequency. I've heard many of you talking about ionospheric effects and things, so you're certainly well aware of this. It's the natural frequency in which electrons oscillate in a plasma in response to a disturbance. So it depends only on the electron density. It's a proportion to the square root of the electron density. So if we have models of the solar atmosphere in temperature and density, we can certainly, as a function of height, so we've got density, this dashed line here is the density falling off as you go to higher heights. And as you go far away from the sun, it starts falling off like here. The details aren't important, but the point is that by having such models, I will know what the plasma frequency as a function of distance from the sun is. And that's one of the things on my diagram. Now, one of the disturbances that can cause this is an electromagnetic wave. So electromagnetic waves can propagate freely in a plasma if its frequency is higher than the local plasma frequency. But if it's lower than that frequency, it cannot propagate. It's going to be evanescent, die exponentially, and cannot propagate. In a varying density like the solar corona, or it's also true in the Earth's ionosphere, if you have a given electromagnetic wave of a given frequency, it's going to propagate into the medium until it reaches a place where, after approximately the electromagnetic wave frequency is approximately the plasma frequency, and then it's going to reflect. And of course, many of you are aware of that. In the case of the solar atmosphere, the plasma frequency can be thought of as a limiting frequency, or a surface below which no information at that frequency can be seen. So if there's some region of the solar atmosphere that generates electromagnetic waves that are at a lower frequency than this plasma level at some depth, you will not see it. It can't propagate to you because those waves are evanescent. So you can only see things on the sun that are going to come from above the plasma level. Okay. So let's take a look at this diagram. And this dark line here is the plasma frequency. So you start out here, plasma frequency in the chromosphere. This is frequency going this way, 7 decades of it. And this is height above the surface of the sun in units of solar radius. And then over here is the height in units of kilometers. So we're going all the way from very, very low in the atmosphere all the way to the Earth. The Earth is sitting out here at 215 solar radii. So this diagram gives you information about the sun and the solar wind all the way out to Earth. So over this 7 decades, this solid line is indicating that the plasma frequency is about 10 gigahertz at the base of the chromosphere. This is above the photosphere. And then the frequency decreases a little bit because the density is going down. And then you get to this very, very rapid drop in frequency. And that's because of the very rapid drop in electron density. So the chromosphere is quite dense, and then you reach this point where the corona begins, and you have a rapid fall of density. And then the density falls off more slowly, and eventually follows this 1 over r squared dependence. It's actually, since it goes, then the density is going as 1 over r squared. So the frequency proportional to the density is going as 1 over r. And so it's just a log plot, it's just linear shape. Okay, so what I'm saying is that the way you read this is that 10 megahertz, say, you will not see anything in the sun that is below a height of around 1 or 2 solar radii above the surface. So all of this region below this line is going to be evanescent at 10 megahertz. You'll only see 10 megahertz coming from or above this line. So this line is a sort of a limiting frequency, which is in a sense a surface. That's the size of the sun in plasma frequency. Okay, so the sun is starting out being very small down here, just the size just above the chromosphere, and then as you go to higher heights, the size of the sun balloons according to this line and becomes twice as big or twice the radius out here at 10 megahertz or so, and becomes even bigger as you go upward. Okay, so that's the meaning of that. The second frequency is maybe a little bit of unfamiliar to you in some ways, but very familiar in other ways. This is the free optical depth unity frequency. So this is f tau equals 1. So it's a complicated name, but it's quite easy to understand. If you look at this photograph here, I guess you can see some thin clouds here. You can see the sky behind it. that would be an optically thin cloud. So if you look at a cloud that's thin enough, you'll see partially through it, and we say that it's optically thin. You can see the blue sky behind it, and certainly if something was inside of it, we would be able to see it. But there are other places where it's optically thick. If there's enough water vapor, it becomes like this. There's actually a surface to the cloud below which you cannot see. So what's happening is that we say the opacity of this cloud has become greater than unity, and so now it's optically thick, and you cannot see what's inside of it. So the division between optically thick and optically thin is controlled by a parameter tau called the optical depth. And optical depth of 1 is the dividing line between thin, which is less than 1, and thick, which is greater than 1. So in the case of a fully ionized plasma like the solar atmosphere, the opacity is provided by free interactions. It means a free electron collides with free ions, which are mainly protons. And so because it depends on the number of electrons and the number of ions, it actually goes with density squared. That's because the number of ions is basically the same as the number of electrons. But the opacity also depends on the speed of the particles. So hot plasma actually has a lower opacity than cool plasma. And so it actually has a dependence that goes as an inverse power of temperature. So you end up with lots of density gives you a high optical depth, but hot plasmas give you a lower optical depth. And so what this is the frequency at which, because if you look at this cloud and you say, okay, it's optically thick, but if you look at it in radio waves, you'll see right through it, right? It becomes optically thin in radio waves. So it's frequency dependent whether it's optically thick or thin. So this frequency, which depends on the square of the density and the square root of the 1 over the square root of the temperature, that's the frequency at which this surface is opaque. Okay, so that line is this gray line. And you'll see that in places it's above the plasma frequency line, other places it's below. So what's the interpretation of that? Basically here, emission would be allowed according to the plasma frequency line, but it's below the optically thick surface. So it can't get out because the corona is optically thick there. So it does propagate, but it ends up colliding and interacting many times before it gets to that optically thick surface. So you really can't see below it. But here, it's the opposite case. The optically thick surface is here, but those waves that at that frequency cannot propagate because they're below the plasma frequency. So in essence, the surface of the sun, what the sun looks like, is provided by the uppermost of these curves. So here we'll see the optically thick surface, here we'll see the plasma surface. Okay? So it's kind of a way of characterizing what you see. Okay, there's one more frequency, that's the F sub B. This is the electron gyro frequency. So you know that in very strong magnetic fields, electrons feel this turning force, and they end up going in circles. And these circles are interesting because a slow electron will go in a small circle, but a faster electron, a higher velocity electron, will go in a big circle. But it's in just such a way that the small one going around its circle or the big one going around its circle take the same time. So it ends up that all of these electrons have exactly the same frequency, and that's called the gyro frequency. It depends only on the magnetic field strength. So they all have the same period, and one of that period is the gyro frequency. It turns out that the gyro frequency depends only on the magnetic field. So if you double the magnetic field, you will you'll have the time that it takes to go around the circle and double the frequency. It turns out, though, that it's not quite that simple because as temperature increases, the velocity of the electrons has to be treated relativistically. The emission pattern, the emission radiation pattern, starts out as a simple dipole pattern, but because of this relativistic effect, it becomes beamed a little bit in the forward direction. And so when you see the time behavior, the time domain variation of the power, it ends up peakier in the forward direction and less peaky in the reverse direction. And that has, therefore, the content of harmonics in the spectrum. So you end up with the fundamental here, which may be strongest, but you'll end up with the second harmonic here and the third harmonic here. So I'm using this letter S to indicate the harmonic, and it's saying then that the gyro frequency is proportional to this harmonic times the magnetic field. Okay, so what does that look like on our plot? We now have these magnetic fields are in the vicinity of sunspots. So if you're away from a sunspot, you can ignore these lines. But when you're in the vicinity of a sunspot, it turns out that, of course, magnetic fields are very complicated, and so the details are going to depend on which sunspot you're looking at. But if you look at collectively all the different sunspots and you say, what is this sort of behavior of the magnetic field as you go outward, it turns out that it's sort of like a power law, which is a straight line in this log plot. And F sub B, this solid line here, is indicating this kind of average behavior of the magnetic field as you go outward. So the third harmonic of the gyro frequency is going to be important. That's lying above the optical depth unity surface, and so the surface of the sun above the sunspot is going to be the surface of this magnetic field rather than the surface of the optical depth unity height. So this diagram, basically the uppermost curve in each place is going to be the one that's important for the type of emission. And in fact, for flares, you actually go to much higher harmonics. So if you're talking about a flare, you can get up to the 10th harmonic, even up to the 100th harmonic. So they can be quite relativistic particles accelerated in these regions. And so then you'll be up here to the, say, the 10 FB or so. So this is showing you what range of frequencies flares will be seen very clearly. So what I've done is I've divided this set of plots into different emission mechanisms. And so here you get gyro resonance emission, which is this the 3 harmonics over sunspots, or gyro synchrotron emission, which is the emission of flares. And then in this region you have mainly Bremsstrahlung, but remember Bremsstrahlung is important. Sorry, I should say Bremsstrahlung and free are the same thing, right? So I've been talking about free, but this diagram was done at a time when I was referring to Bremsstrahlung, but they're the same thing. So the free emission is coming anywhere there are no sunspots, then you can ignore these lines and just go with the optical depth unit. Okay, so those are the 3 frequencies. So now I want to go ahead and go through the decades one at a time. So we're going to start out with the metric decade, which is kind of in the middle. And let me just show you quickly here. This is the region I'm going to be talking about now. So you might ask, why did I start in the middle? But that's because that's where solar radio physics started. The first discovery of solar radio emission occurred during World War II, and it was the radar jamming in England, and it was noted in a memo, a wartime memo by J.S. Hay in 1942. And this emission was very much a concern because normally the Germans could jam radar and they could tune it out by changing the frequency of the radar. You just dial a tuning frequency and keep going. But this particular emission couldn't be tuned out over the 55 to 85. So it meant it was a very broad jamming. And of course this was a big problem if the Germans knew how to do that. But it turned out that indeed by looking at the timing of the jamming and the direction, the azimuth of the jamming, it could be connected to the sun, and they realized that there were very large sunspots on the sun at that time, and so they put it all together and understood that the sun was doing this. Around the same time, in New Jersey, at Bell Labs in New Jersey, the quiet sun emission was reported at 3.2 centimeters. This is up in the microwave range. But it wasn't published until 1945. At the end of the war, there were a lot of surplus radar equipment around, and researchers, especially in Britain and Australia, began a concerted effort to study this newfound radiation from the sun. And of course, they were realizing then that other sources in the sky, such as SIG-A or CAS-A, were radio sources. So there's a huge effort then to try to understand this kind of emission. Major discoveries in the case of the sun included interferometry, and that was using a Seacliff interferometer at Dover Heights in Australia. And so they got the direct radiation from the sun, and then they got a reflection off from the sea. And those radiations arrived sometimes in phase and sometimes out of phase, so you got destructive or constructive interference. So this is actually a trace of the rising sun as it went through these periods of destructive or constructive interference. And this is another day when there was some bursting going on. So you had the overall profile of the rising sun and then some bursts going on top of that. It was very interesting that one of these early papers actually did describe the idea of connecting this to a Fourier component, and to put several of these together you could actually determine the distribution of brightness. So this was really the beginning of the idea of interferometry. They also used this data to measure the million-degree corona. So before then, they didn't understand that there was any brightness of 1,000,000 degrees associated with the sun. They also found that the sun is larger at radio frequencies, and they discovered this frequency drift of outward propagating exciters. So this is a couple of traces at multiple frequencies. And this is time going this way. This is about 20 seconds of time. And this is frequency going from, looks like about 60 to 120, 130 megahertz. And at higher frequencies, the emission arrived first and then slowly moved, actually quite quickly moved to lower frequencies. And then there was another type of burst, it's so-called type 3 burst. And then there was a type 2 burst, which is a slower drift. And it was understood quite quickly that these were due to nearly relativistic electrons streaming out from the sun, these type 3 bursts. And the slow drifters were the shock wave type 2 bursts. So I'll be talking a little bit more about those as we go on. So anyway, this is the region of the spectrum we're talking about. And you'll see that the plasma frequency is uppermost, you know, at the tail end of this, but at the higher frequency range, the optical depth unity surface is there. But during bursts, you have to realize that these plasma frequency generating bursts can be seen even through quite a bit of absorption. So even if it's below this optical depth unity, if they're bright enough, they can be seen. Okay, so that's that range. Let me give you sort of a modern example of an observation here. This is from the Owens Valley Long Wavelength Array. This is by Greg Helen and his group at Caltech. And it sees the whole sky all of the time, but the sun is in the sky, so we get to observe the sun as well. And this is a burst that occurred in 2015 during some commissioning observations. I'm going to just show you a little movie. This is the quiet sun. The actual disk of the sun, much bigger than the photospheric disk, right? Because we're at a low frequency where now the source surface is, at this frequency, is going to be mainly the plasma frequency. Although, due to variations in the density, some of this could be free surface and some of it could be the plasma surface. But as we watch the movie, this trace along the bottom is showing the brightness. And I don't know if you saw momentarily a type 3 burst, so there'll be another one right there. So you see just momentarily a bright source. And then over time, there's an eruption going on, and over time, this burst here will appear, and it gets brighter and brighter and brighter, and eventually wipes out the weaker sun, so you cannot even see the sun anymore.
That's in the corona?
That's in the corona. So it's now well off from the center of the sun. Now, if we look at a plot of where these are located, This is actually just a coronal mass ejection just sticking out above this occulting disk. You know, for the space-based coronagraphs, you put a big occulter in front of the sun to block out the brightness, and then you can see the corona around it. But that actually extends to 2 solar radii, you know, 1 solar radius to the surface, another solar radius up to here. And so this is a coronal mass ejection just peaking up here at this time when you see these sources at 2 different frequencies. If you look in the spectrograph, you see that you've got these type 3 bursts here that are these streaks, vertical streaks, and then this more slowly drifting type 2 burst, which is associated with the shock wave. And if you extrapolate that backward, this sort of dotted line is supposed to indicate the timing of that. Now, this spectrograph record is coming from another spectrograph with no spatial information, but the Owens Valley Long Wavelength Array was observing in these 2 bands. I don't know if you can see very clearly, but there's a little bit different color here and right here. I've scaled the record from this instrument to more or less match the brightness of this one. But if you zoom in on that, this is the, in those 2 bands, is this one. The reason it's 2 bands is because, again, it was during commissioning and these ones were giving problems, these intermediate frequencies. So this is 70 megahertz at the top, 50 megahertz at the bottom. And, but this is a very long period compared to this. I have to squeeze this down into this. This is actually the same period as that on this diagram. So this is now a couple of hours long. And you can see that in this record, you see only a few type 3 bursts and this type 2 burst. But in this record, their emission started much earlier and lasted much longer. So this is far more sensitive than this one and allows you to see this long-lasting emission. If you look at this is supposed to indicate an image here at this time, a quiet sun before the event really starts. And then during the event, I don't know if you can see, there's some contours of this that aren't coming up very well, but this is the contour of this image, and then there's this noise storm out here, and then at this time is another type 3 burst, which is occurring here, and then we go back to the quiet sun after it's all over. So let me just show that, I can show that movie one more time. The plus signs are kind of giving you a lag. The last 20 images, the center is shown with the plus sign, so you can kind of see the time development again. But again, this outward going burst associated with a coronal mass ejection occurs right there. So what we want to do, of course, is to find where these shock waves are in relation to the coronal mass ejection. And the only way to do that is to use these radio measurements to do that. Okay, now let's move to the next frequency range up, the decimetric range. So now we're talking about 300 to 3,000 megahertz. And here you see there's a lot going on. You've got the plasma level is quite varied under the optical depth level, but you've got some gyro emission coming in here as well. So in this range, it's perhaps the most complicated phenomenon of all because all 3 mechanisms are volume predominance in various ways. This is an image from our array here. This is our array has been being constructed over the last 5 years or so. It's an upgrade to an existing array, and we've finally gotten it to the imaging stage. And so this is actually one of our images taken in April compared to one of the STO extreme ultraviolet images. So you can see that we've actually got 3 sunspot regions showing up, one of them just at the edge of the limb. We've got some other little sources here that are side lobes of the brighter source. So we're still working on image fidelity here, but there's a lot further we can take this. But you can see the disk of the sun there in the radio, and it's larger in size than the photosphere, simply because this surface is now moved out. The optical depth unity surface is moved out. So near sunspots, though, the magnetic field is very strong, and it's strong enough that the opacity is high in the corona, so these are at 1,000,000 degree or so temperatures, and so they're becoming very strong. The bursts themselves can occur in this range. Can be either gyro emission, which is just the normal solar emission, or it can be plasma emission, this coherent emission from the electrons oscillating. The plasma emission is much brighter, so when that occurs, it's sort of dominating the emission. But it can occur in a startling range of varieties. So these are some records in this decimetric range of something called a zebra burst. You can see these stripes in the spectrum. This is a spike burst with a bunch of very, very short duration, very narrow band spikes that are occurring. This is from a maser mechanism, actually. And then you can have these fiber bursts, which are so-called intermediate drift bursts. They're drifting from higher frequencies to lower frequencies over about 6 seconds or so. So all of these things were described in the 60s and 70s on the basis of these spectrograph records. Again, time going this way and frequency going this way. But we would like to be able to image these, to be able to see where they're coming from, and only now is that becoming possible. So I'll be showing you some examples of that. The slowly varying component, as the sun rotates, of course, these things are moving. That slowly varying component of radio emission and its connection with sunspots was actually discovered as early as 1947 by Covington in England. Okay, so one of the things that's interesting is the spike bursts here. It turns out that those spike bursts, there was one on 2006 December. It's supposed to be decimetric. I think the spell checker did that to me. Decimetric spike burst was the strongest burst on record. It actually reached 1,000,000 solar flux units, and a solar flux unit is 10,000 Janskys. So we're talking about 10 to the 10 Janskys. The radio noise was so strong that it knocked out global positioning system reception on Earth everywhere in the southern hemisphere for about 10 minutes. And I'm going to show you a report that a little movie associated with a report at that time. So what we're seeing is all of it's an array of GPS systems, and then as the flare goes on, they start turning red everywhere in the southern hemisphere. So this is actual data from these network of GPS receivers, and whenever they go red, it means that they have lost lock on the satellites. They've lost. You need to be able to track at least 4 satellites for a proper fix of time and location, and so they've lost lock at those times. So that was discovered by a colleague of mine. Who's actually a grad student at the time at Cornell, and we used our Owens Valley data to connect that with the solar radio emission. So it was definitely the solar radio emission itself was causing the interference that resulted in the GPS receivers not being able to see the satellites. Another source in the sky that was stronger at the same time. Currently, we have some exciting new capabilities from the VLA in this range from 1 to 2 gigahertz that have allowed allowed imaging of some dynamic illumination shocks. So I'm going to show you. This is a spectrograph record again, similar to what we've had for many decades. This is time going this way and frequency going this way, increasing upward. And you can see that there's an overall drift of the spectrum, at least this edge, down to lower frequencies. So that's a slow rising of some flaring loops that are, as they connect, they rise very, very slowly. And so the frequency at which this emission occurs is going down as well. As they rise, the emission goes down. But during this time, we have actually spatially resolved information about it. And what we see is that this is as a function of frequency. They're color-coded at frequency, but you can see spatially they just kind of blow apart. And it turns out that what's happening is this thing here is indicating a plasma blob that is seen in the ultraviolet. And that plasma blob is coming down and basically interrupted this linear relationship of these curves. And this is a model, this is the magnetic field in the model, and this is the density of a jet being coming down. So the idea is that above this, there's some reconnection of magnetic field, releasing energy. This plasma is moving downward. It's forming a shock wave at the bottom where the new loops are forming. So they close and they form a loop, and this jet hits the top of the loop and forms a termination shock. And at that termination shock, you have a relatively stable set of radio emission until this plasma blob comes down and then explodes it and blows it apart. And this simulation is supposed to indicate this plasma blob arriving and disrupting the shock. And this was reported in 2015 in Science. So some really interesting stuff coming from things like the VLA, which now have the ability to make very short duration images in very narrow ranges of frequency across wide bands of frequency. So by combining all of that, you get this kind of phenomenal picture. Okay, so now we move up to gyro resonance. We're moving up to the microwave decade. So this is 3 to 30 gigahertz. So we're now talking about centimeter wavelengths, 1 to 10 centimeters. And here you can see that plasma emission is sort of over. You're not really getting much plasma emission. You're getting, in the quiet sun, you can see a little bit of increase in the size of the sun due to this optically fixed surface rising. And you also get the magnetic field. In the regions of magnetic field, you see brighter spots, as I said before. And of course, solar flares are going to be strong. When they go off, you're going to be seeing strong emission there. So in this range, the emission is free emission everywhere, except near the sunspots, where it can be dominated by gyro emission. And the harmonics, again, are up to about the third harmonic during excluding flares, and then they go up to higher harmonics and you have flares. So higher frequencies are going to require higher magnetic field strengths, but eventually the frequency exceeds the highest available magnetic field strength of about 2,000 Gauss, and the emission reverts to free. So what I'm talking about there is at the very highest frequencies, you see this 3FB line falls below the optical depth unity surface, even in the presence of sunspots. So at the higher end of this frequency range, sunspots will no longer be bright. You'll see the plasma surface instead of this magnetic field surface, which is normally higher. Okay, so it's possible to use multi-frequency imaging to deduce the coronal magnetic field strength, which is only now becoming possible with radio instruments such as the VLA, our instrument in EOPSA, and a couple of others, one in China and one in Russia, that are coming along with some of these same capabilities. So this is actually a movie of the rotating sun at 17 gigahertz from Nobiyama radioheliograph. This is a radioheliograph in Japan, which is still operating, but its biggest problem is it only operates at 2 frequencies, 2 narrow frequencies with widely separated. So we can't look at the spectral behavior, but it makes a very, very nice image. So let me run that one more time. You can see all the features of the surface. You can see the filament channels here. You can see actually on the edges of the sun, you can see some prominence material sticking up above the limb. And of course the active regions. These are not magnetic bright features like I was showing before, but these are simply hot because they're in active regions. So it's hot, but it's not the coronal brightness. It's still chromospheric. So you're basically seeing the chromosphere at these frequencies. With our instrument, EOS, I remember I showed you that one full disk image with several active regions. This is the same, these are the contours from that same image. You have 3 active regions, and then you have in the background the extreme ultraviolet image from the Solar Dynamics Observatory. But what I want to do is show you something about the frequency dependence of these. So on this next diagram, these are, with EOS, we're observing at hundreds of frequencies, not just 1 or 2 broad space ones. So if you collect some frequencies here, this is 2.9 gigahertz, 3.38, 3.489 gigahertz, and as you go to higher frequencies, this particular active region is getting fainter, weaker. And that's because the magnetic field strength is basically dying out. It's not high enough magnetic field to support that third harmonic emission at this frequency of about 5 gigahertz. Whereas this active region, which let's point out, this one is the stronger one, and this is the weaker one over here. So if you look at the stronger one, you can see that at 5 gigahertz it's still going strong. It's nice and strong there. In the background is a magnetic field map made from surface measurements. So we're looking at photospheric measurements to make that. So what we're doing is we're looking at the radial dependence of the magnetic field in the corona above the surface. And there's a huge interest in the community to understand, we make the measurements in the surface, how do we extrapolate that into the corona to find out what really is going on? After all, it's in the corona that these flares and instabilities are occurring that's driving all this solar activity. So from these observations, we'll be able to actually measure coronal magnetic fields, the magnetic field at some height above the surface. So that's an incredibly important thing that we've been working towards for 5 years or so. Now, in the case of flares in the same microwave range, this is a simulation of a flaring loop, and this is a function of frequency going to higher frequencies as you go down. So you end up with a loop that is, again, a simulation of radial brightness in the whole loop, and as you go down in this diagram, it goes from everywhere in the loop to kind of dominated at the peak, at the top of the loop, and then eventually becomes dominated at the foot points of the loop. And those are variations of the energies of the electrons and also the magnetic field in the loop. But it turns out that you can tease all of that dependence apart if you have spatially resolved spectra. So what I have here is if you take this loop and measure the spectrum at different locations, you'll see that the spectrum, they look like the same shape, but they have a shift in the peak frequency. So at this, down here near the foot point of the loop, the peak frequency is quite high, up around 15 or so gigahertz. And then as you go to up the loop, the peak frequency is getting to lower and lower frequencies. And at the top of the loop, it's around maybe 5 gigahertz or so. From that information, you can actually measure the magnetic field. So we know that the magnetic field in the corona above this area is around, it's at 586 Gauss or so. And then up here, it's only 145 Gauss. And then again, it grows to higher magnetic field strengths there. Also, the polarization is changing. Here you have blue dominating, that's like right-hand circular polarization is dominating. And as you go down here, the left-hand circular polarization is dominating. So that's telling you that the polarity of the magnetic field has changed from one end to the other. And from these spectra, you can measure the magnetic field. This is a magnetic field map actually created from this simulation. And then here's the angle to the magnetic field, so that's telling you what the angle to the line of sight is. And then this is something to do with the energy of the particles that are in this simulation. So EOS is designed to exploit this technique to measure magnetic and electron parameters on a 1-second basis. So every second we'll be able to measure the variations of magnetic field and particle energies. And it does that by rapidly scanning across the entire 1 to 18 gigahertz spectrum using broadband feeds. But EOPS has only just come online, and already our observations are showing, for one thing, that the emission is not confined to these nice small loops. These loops are implicated from hard X-ray observations where the particles get into those loops and they're sort of confined to the loops. But in fact, what we find when we look at actual data, and this is data from April this year, is that those particles get out of those loops, they go everywhere. And although they're too few and at too high energy to really see in other wavelength ranges, but we see them in the radio. So what I'm going to show you here, I wonder if we could dim these lights. Is it possible to? Okay. So what we're seeing here is, again, from the Solar Dynamics Observatory, the background, you're seeing some sunspots and some brightenings here that are the flare emission as seen in the chromosphere. And so as that flare goes on, I'm going to be overlaying with some black contours that are indicating our observations from EOPS at 3 frequencies. So this is a low frequency, an intermediate frequency, and a high frequency. And this is the actual spectrum. So this line here, this white line, is going to indicate where in time we're actually making the measurements. So let me go ahead and go. You can see the line marching across, and you can see the emission at the different frequencies. So the spatial distribution of that emission is what we're interested in. Let me go back and run it one more time. And I just want to point out that the low frequencies are covering the entire region here, whereas at high frequencies, they're mainly around the flare site, which is shown up in the chromosphere, but also around the sunspot region. And then in intermediate frequencies, if I play it one more time, you can see that there is a source that appears over by this other sunspot. So these electrons are not confined to small loops around where the chromospheric emission indicates, but actually are finding their way all throughout this region. And that can be important because these are the sites of these coronal mass ejections. And those coronal mass ejections, if they have these high energy particles entrained in them, then as they move out, those particles can be seed particles for further acceleration by the shock wave as it's moving outward. So this is a little bit, not terribly surprising, but it's a really nice demonstration that the radio emission is showing us something that's not visible in any other wavelength range. So it's something really neat. Okay. So I think I'm probably moving on here. The next range is the high frequency range now of the millimeter decade, and here ALMA has opened up the picture for solar research. And so this is actually a full disk image in ALMA, from science verification data that we're taking. ALMA has only just now been opened for solar observing. So prior to a year ago, although it had been observing other kinds of sources, it wasn't allowed to propose for solar observing. So only in the last year we've gotten some solar data. So this is a full disk image from a raster scan. It's actually some kind of double circle raster of the sun at 3 millimeters. And then this is the same thing at 1 millimeter. So these are fantastic, but each resolution element there is the primary beam of the instrument, and within that we can do interferometry. So this is a part of a field, a circular field from ALMA at 3 millimeters, 100 gigahertz. And what I'm interested in is to look at the variation of this as a movie. So let me run the movie, and you'll see that things look pretty chaotic. It doesn't look that clear what's going on. But if you look in other wavelengths, you can see these waves running around inside the sunspot. You see those waves coming and going. And so if we take a cut across this region and we compare the way that the emission brightening and darkening is occurring over time, we can make time plots like this that are actually showing the brightenings and darkenings that are very cyclical. And these are these running waves inside the sunspot. They occur at a 3-minute period. And so what the sun is producing all kinds of acoustic noise. But in the sunspots, there's like a cavity, a resting cavity, where this 3-minute oscillation can survive. And all the other ones are kind of dying away, but the 3-minute oscillation can survive. And so this is the ALMA data. These lines are to indicate the sunspot edges. And so this as a function of time, you see these things coming and going. And then this is in some of these other spacecraft data and from some hydrogen alpha on the ground. And now if you make a cut, this is a cut at line position 229, which is just here. So if you make a cut through all of these, you get these line profiles, basically time profiles of the oscillations. And ALMA is down here, and you can see very nice oscillations. And perfectly timed with that, here's in hydrogen alpha, you see very similar behavior. And what's interesting is that the timing of this is very much at the same time as H alpha, but if you look off the center line at the wings of H alpha, the phasing is actually backwards, so that the hydrogen alpha center line is peaking here, and that's actually the dip of one of the wings of the H alpha. So by looking at where H alpha is formed at different heights and where the ALMA variations are in phase with it, we can kind of get an idea of what height the ALMA data is coming from. So this is brand new stuff that a graduate student and I are working on. So I'm probably at the end of my time, right? So, let me just very briefly mention the lower frequencies here. I started at the metric and I went up, so now going back down. This is a region of mainly plasma emission, and we're actually at heights now of around the solar radius above the surface, up to about 10 solar radii above the surface. And I won't go through all the details here, except to say I refer to this as the lost decade because it's actually below the ionospheric cutoff frequency, some of this, right? And so we cannot see some of this from the ground. This is something that, Dr. McCain was mentioning in his talk, that this is a region that we need to be in space in order to see. And in fact, he mentioned a CubeSat experiment at MIT Lincoln Labs towards this. I'm actually the PI of that mission. This is a mission called HERO, Heliophysics Radio Observer, and it's a collaboration with Haystack and Lincoln Lab. And what we're interested in there is to observe in this region of heights in the corona that we cannot see from the ground in the radio. We need to be up in space for. And this is a nice movie of a CME, a coronal mass ejection moving outward. And you can see the location of some bursts as it moves outward. This is actually from the Malura Wide Field Array Observatory in Australia. This is courtesy of Divya Oberoi. Let me just show you that one more time. So this is like the shock wave range, and you can see that that emission is actually following that thing as it moves out. So this is a shock-related emission. This is the type 2 burst emission. that is going from higher frequencies to lower frequencies relatively slowly as a result of the shock wave. And we want to move that out. We can do this from the ground at low heights, but we want to move it out into this range, out to 6 or so solar radii. And this is the cover page of that, proposal. We have actually 6 CubeSats. They're all 6 units in size. And they would have this kind of cross dipole. It's what we call a vector sensor. And they would be able to observe at these low frequencies, actually going all the way out to a radius from the sun of 100 solar radii. Okay, I think I'll go ahead and end it there. We can obviously follow these things out into the interplanetary medium. If you go to even lower frequencies, you're going further and further out. And so this is something that has been done from space, but without much spatial resolution. There's some rotating dipoles that can sort of locate these things, but not really image them. So our hero heliospheric radio observer would be able to actually image them. Okay, let me go ahead and conclude. So basically, we surveyed 7 decades of frequency and 7 decades of history. My own involvement is almost 40 years of that now. Working as a grad student in Colorado and a postdoc and a senior research fellow at Caltech, and now at NGIT. And I'm very privileged to have been able to make contributions in all of these ranges. My involvement actually at the ends of the spectrum, both millimeter and these kilohertz wavelengths, are very recent, basically in the last couple of years. But, although the technologies used in this vast range of electromagnetic spectrum are very different, and the range of solar phenomena that occur are very different. The simplifying framework of these 3 characteristic frequencies provides some kind of a guideline. So if you look at that diagram, you can really get a sense of what's going to be important in which frequency range, what sort of heights above the surface they will be important. So I hope that I've conveyed some of the excitement of the recent developments in dynamic imaging spectroscopy, and you'll certainly be hearing a lot more of that from us.
Are there any questions?
Back here.
Hero is very interesting, and it looks like it's got a lot of potential. Can you say when the launch will be, and also how did you arrive at that antenna design?
This is a proposal to NASA, and so the announcement of selections should be any time now. It's supposed to have been in the spring, and we were told summer, but I don't know what summer means exactly. We really expected to hear by this month, but so far nothing. It's a big competition. It involves a lot of different, it's mainly heliophysics, but it can be lots of different experiments. So I don't know how successful we'll be. I do know that there were 2 other very similar science proposals, one from JPL, one from Berkeley. So a lot of competition. So we'll see. I don't know. But if it does go, the launch date would be like in 2022.
Are you using magnetic loops or Moxon?
Yeah, this is called a vector sensor, and so it has both electric dipoles and magnetic loop. And the Lincoln Lab guys are developers of this. Right now it's at very low TRL level, so it really needs to be flown to improve that. But they claim that it will be able to locate just with a single element with quite high precision, and then by using interferometry of multiple elements, we'll be able to actually image the sources.
Is that with Frank Roby at Lincoln?
Yeah. Okay. And the director, Colin Monsdale from Haystack.
Can
You go into geosynchronous orbit with those?
It's a near geosynchronous orbit. It's one of those things we want to be able to. We can't go in geosynchronous because a lot of people get all excited when you add six new things in geosynchronous orbit. But the idea is to be a little bit lower than geosynchronous orbit and then drift, and then move to a higher orbit and drift the other way, but always staying away from the actual geosynchronous orbit. It's a kind of an ambitious orbital plan.
Which rocket are you riding on?
It hasn't been decided yet. It needs to be a ride to GEO, so there's some. I forgot now the launch provider. They did contact one that had some. They weren't willing to guarantee anything, but they expected to be able to provide the rides. I think there was a.
Thank you. So. Going along the idea that the same principles that you described for the sun apply to all stars, and with amateurs wanting to contribute in a sort of a citizen science kind of way, what recommendations would you give to us putting together small telescopes looking at other stars and trying to make good observations in this radio spectrum? How should we do the observations, and where should we look to have the greatest impact for observations?
Yeah, I think if you just scale solar events to distances of stars, you'll never see them. So you actually need something like a super sun going on. But it turns out that there are some bursts. Certainly the brightest burst I mentioned here was a maser mechanism, and there's a similar maser mechanism that occurs on Earth and also on Jupiter, so you get those kilometric radiations that are very bright. And there may be something similar in other stars. So what you want to do is you want to go to the appropriate frequencies where those will be strong. That's going to scale with density and magnetic field strength. So for stars, there will be higher frequencies than for planets, for example. But you definitely want to go to frequencies below a gigahertz, so somewhere in the decimetric or metric range. And we can expect that some of these events may show some drifting in stars. There have been some reports of that with the VLA, for example. But they can be bright enough to see with individual dishes. You still need quite a bit of, there may be 100 millijansky range or something like that. So, but I think that's probably the right place. And maybe some extrasolar planets can have Jupiter-like emissions or something, so there's some interesting things to look for at least.
What is about the size of the sun effectively at 408 megahertz? Does it change with solar activity?
Well, you can look in my diagram. So 408 megahertz. So here we're talking about the one that's important is going to be the optical unity one, which is going to be right in here. So it's maybe it's several tens of kilometers, tens of thousands of kilometers larger than the surface. So it's really not that much bigger at 408 megahertz. But it will be a surface that is not perfectly spherical. It will have some bumps and wiggles depending on solar activity. And absolutely the shape and brightness will vary with solar activity.
Yeah, I'm wondering what to expect. I have a receiver at 408 megahertz and I've played with it for quite a few years, and thinking about putting an antenna up that either tracks it or has a wide enough beam width that will catch it and watch it during the eclipse.
Yeah.
And the area I'm in will get about 95% eclipse before I get the receiver set up. Will that make an interesting effect?
Yeah, and I think it'd be fantastic to look at the time profile. And what you can do is look at the differential of the time profile, because if the moon is covering an active region, if we're lucky enough to have active regions on the sun at that time, then you can have a sudden drop, and that will appear as just an inflection point in your light curve. right? But if you take the derivative of that, you can actually see the up and down of the, as it crosses such a region. So it might be interesting to do that.
Thank you.
Matt, any question?
Yeah, just one more.
Yeah.
So, sorry.
Proton doesn't do anything?
Protons do all kinds of things. It's just that they're not visible in the radio. The problem is
It's not, yeah, right, I understand, yeah, that's understandable. But
yeah, they basically, the power it goes as the acceleration squared, right? And the acceleration goes as a ratio of the masses. So you end up with this factor of 2,000 or so difference in the mass of the proton and electron. You have to square that. So you get like 1,000,000 times less emission from an equivalent proton than an electron.
even with the sun, okay.
Yeah.
Thank you.
Thank you, Professor Gary.
We wanted to say thank you.
You need to move, he's got some projection on his forehead, that's not gonna look good in a picture. Come up a little closer to the
Or
camera.
off to the side.
Yeah, that would have looked terrible.
That's better.
Another one.
Okay, let's take a break. We meet at 3:15.
That was a wonderful experience.
Yeah, you know, some big question.
Thank you.
Because those had some discussions last I don't think everybody's telling me it's not very good.
The one you went to at NASA?
And the hydrogen. So that, what kind of targets can we get? There were some other ideas too. They were some slides. And also the calibration issues. So what they were saying then is, we have a means to
you have to go before you reach another level. So you can make your baseline really, really low and
so I got a couple ideas out of that to work further on.
one way just keep adding it up. You don't want to short of the wavelength here. Half the wavelength, half the wavelength. Somebody wants to
Yeah, I love somebody who wants to
right here.
What it's really all about is
or any telescope does.
Let me see.
And you're only going to get in trouble if you have multiple sources.
So the other way taking it is some of the targets mentioned. Because that building is
So if I can get to your home. If I can get to your home. Okay. Yeah, promise.
Sure. Let me give you my name and address. A map is like these to get the.
I have your email address.
I'm not on the list. Oh. Did it make sense? For a reason. Temperature was too low.
But when you start looking
I could say that was
One of the
at actual signals,
mistakes we
the temperature at.
because I should have given
it's
this.
not just the figures you're pointing at.
And that was giving folks a year.
Yes.
Yeah.
So even though you look at two sources,
That makes sense.
They will tell you, it's going to be
unless they're
live
both
project.
Third, two.
Oh, my God.
So, we're going to This,
So I have somebody way of contacting.
2 weeks.
Folks, I didn't say you lived.
No, there's 2 hours in there, that's good when they use it up.
Yeah.
So I can't do these scans, take 20 minutes each. Jay Wilson, he says he has access to
Right.
I'm going to go marching around.
You're going all the way from New York to Alaska? Oh, okay.
No.
Okay. Otherwise, that's a trip for you.
Take 2 days to get that happen. I'll have a day before. You're not throwing arms to set.
Right, so you basically.
Okay.
That'd be good. But like I said, I don't have the kids.
Yeah, that's okay.
That's process.
So you don't have to, I'm pushing myself around, you know, the hydrogen alpha, I do this work out of huge cell messed up for family as well.
Well, that's the nice thing about things, it's passage.
Yeah, that's good.
Set it up, and then you can go look at the clips.
Right.
You don't, you just walk away. Because I don't want you to miss the visual.
Yeah.
Because you're sitting there between dogs or something.
No, yeah. Already been warned about that. Yeah, well, what I'm gonna do is take that fully off. I'm able to be.
I've seen it in the
Targets can be
don't even try. Because you're going to spend so much time fitting with your camera.
Yeah.
That you're going to miss it.
Well, they've got software.
People have that.
So
Our observers, how long do they observe? Or is their data just conceptual and not
The only real observation was me
Professionals do this a lot.
yeah,
How to do this.
Yeah.
And even for them,
yes, yeah, the needs that come from the professor before his wife told him.
but everyone else is just kind of like,
The one between the two of them,
They don't have some kind of target to do it. They point at something and they're not really maybe thinking.
that's sweet. Do not use it as a camera. Application.
Yes.
So here.
Yeah, well, yeah, then we can press the targets here.
There's warnings.
I was thinking, whatever Dan does, he needs an observation about it. He wants to charge people to use that. They're gonna go in, they go lose. Unless they can see the change for observation.
Maybe the back, as I said,
Lose their eyes, yeah. You know it.
Yeah, it's like strapped on so people just can't see it because I was what you know with that? I was afraid all the time. I'm worried about the kid's eyes.
Under your radio that talks to the phone, you don't have an English.
Not right now.
If they're talking about it or.
Actually interesting. Okay, how do you like cash?
Let's get it done, yeah.
Let's get it done.
Yeah.
So now we have a group professional Bible. And that should be yes.
Also, he was talking about quite a long period of recording this. Before even.
Yeah, you take your so like you saw this lesson.
So how much data is that? You're recording audio at
16 bits.
Okay.
You're talking on it. It's not.
Sure.
Yeah,
It's old, yeah.
Yeah. But that's
Good luck with that. Wouldn't be before because of the I'll probably take them up. I don't know what it
Okay, that's fine. I thought it could stay.
Oh, I'm sorry, I'm sorry. No, it could, yeah.
That was good talk. That was complicated. Let's see. So
So our next speaker is Dr. Dave Fields. More, I guess, orbital object information here on radio astronomy and light sail research with small satellites.
Okay. Oh, we got the old title. Okay. Okay. That was more ambitious.
Maybe we can use I can.
Okay, so what we're doing here is putting aside the way I'd like to give a talk, and I'd like to say, here's something we really have to measure, and just launch right into, okay, we can do that with this type of equipment that other people have worked on that we understand, and here's how we tried to put it together, and here's how it failed, and here's how it worked. And here we're kind of looking ahead in a different way, so I thought I'd start out based on what our last speaker did, when he came to the end and said, wow, here is this whole region that we can reach out and study if we go above the ionosphere. And the same thing that Dr. McCain said when he was pointing out, wouldn't it be nice to be able to do radio astronomy from above the ionosphere? And to me, it's a great thing for SARA because it says each of us in SARA then could not only access that data and interpret it, do our own comparisons with what other people are getting, but we can actually design experiments. So it's kind of fascinating. Okay, let's see where we can go with this. And it's supposed to stimulate questions, so if you were interrupted. So I thought, if we're amateurs doing radio astronomy, we don't have a big pile of money, but we have ambitions. So how do we choose what to try to do? We want to have success, we don't want to waste our time. So where are the challenges? And then what is the solution? If we identify these challenges, and then how do we implement the solution? We don't want to waste our time. Well, the challenges come from the science. So where's the science? Spatial. The answer is going to be everywhere. And where's the signal? From the science, but also what's the spectrum and what's the temporal characteristics that we might want to investigate. And that's not all because our enemy. But here the challenge is the noise. So if we want to do something in the spectral region, which is tempting, it's very noisy, we have to worry about it. And from all these come opportunity. So science is basically everything. The universe is a very rich place. It provides us lots of science, lots of challenges. This is 408 megahertz, the sky. And we see a lot of physics. We see challenges making measurements. Can you folks see this, or should we turn the lights on? This is good? Okay. Can you hear me okay? Okay, back. So this is 408. And when we look around in different parts of the spectrum, different other parts, we see science, we see similar physics, but we get a different picture of it. So looking at different spectral regions gives us different information. And once again, it's just a follow-up from what you already know from the last presentation, which I enjoyed very much. So this is basically 5 gigahertz. And it's not the entire sky. It's about a 35 to 45 degree section of the sky. But the universe is a fine stimulating place. Now, why would I use a crappy slide? This is terrible. This is awful, okay? What's going on here is wavelength is increasing left to right, which you've seen a couple of plots like this. It's not that much of a surprise. And this is ionosphere transparency. And everything is light. All the electromagnetic spectrum is just a variation of light. The light we use with our eyes is in the optical window. The light we use for studies slightly longer wavelength, where the molecular windows occur in the atmosphere. In the infrared, that's valuable to us also. Let's study our atmosphere and the components of it. Let's just look at different planets and speculate on what their atmosphere could be. And the atmosphere stays fairly clear down below that into the radio region, but not the ionosphere. So if you say that's part of our atmosphere, well, that's a little bit of a curse because everything below, some say 10 megahertz, everything below that is, according to most radio astronomers anyway, is reflected. So, blessing and a curse. We cannot do radio astronomy, according to most people, below this 5 or 10 megahertz. And if ever we get above the ionosphere, we're shielded from some of that, and we start perhaps seeing interesting things. So, basically, why is it a crappy slide? We've known this a long time, but it's very important. And this is what Krauss published. He had a cleaner picture, but he's one of my heroes. He's a great scientist, a wonderful electrical engineer. He was creative, he did fantastic, groundbreaking work. Okay, so kind of to think of what he did. And the reasons, a couple of reasons that the ionosphere is so reflected on Wilson has to do with generation of Langer waves, plasma waves. And this is just kind of a result of it. You have the electrons, if you push against them with a steel plate, or with an electromagnetic wave or E field, then they're going to push back. They have mass, they have a restoring force because the electrons interact with other electrons. So that's why you get E squared. And En is the number density, how dense that it is. It's permittivity of free space and the electron mass. The protons are important. They're there. It's kind of neutral plasma. But the protons, they're massive. They don't respond very fast. They have their own proton plasma frequency. We don't have to worry because this is the higher frequency. And not 10 megahertz, but 2 to 5 megahertz. It varies because N varies. E's pretty constant. So the number density is constant. This is just the cyclotron resonance of electrons spiraling around the field. And what this is, if we are operating below this frequency, and it's kind of an easy thing to calculate, that below that frequency, then we're going to get an interaction between the EM wave and the spiraling electrons. It's not necessarily bad, it's just interesting. We can lose a lot of energy, we may gain energy. It's an intriguing physics, and that is relevant also. So we have a reflective atmosphere below around 5 megahertz, 5 to 10, and for other reasons, it's an interesting atmosphere below that number. How about the noise? This is jumping ahead a little bit. This is QRM. That just means man-made noise. And this shows the breakup and use of the spectrum. The top section is 3 kilohertz to 300 kilohertz. The middle, 300 kilohertz to 3 megahertz. The bottom, 3 megahertz to 30 megahertz. And it's just awful. But if we get above the ionosphere, some of this is going to go away. So bear that in mind. If we got above the ionosphere, do we hear anything? And the most obvious thing is, look what Voyager detected. Jupiter is a major emitter of radio signals. And just like the Juno mission, 5-year mission, the motor will go from Earth and explore Jupiter. Juno is getting us lots into that. But the Jupiter emission is pretty great. Actually, it's far bigger than you might expect, but Jupiter cuts it off. And then, for other reasons, Jupiter doesn't emit very much by these mechanisms of power frequencies. But there's all this down below 10 megahertz, that we might be looking at. We think of ourselves as the amateur radio astronomers, and we look around the room, and the majority of us look at 4.8 megahertz or 1.4 gigahertz, or we try to do things. But if you actually look around, no, the majority of radio astronomers don't do that. They look at 20 megahertz. At least they probably think they're the majority. They look at Jupiter. And the bigger majority is doing planetary radio astronomy at superset frequencies. There are a lot of superset units around. So kind of interesting. I love our atmosphere. We can do some other physics. So frontier for SIDS receivers. is out there. It's a wild place. If you look out there, and what you have to look at, here's frequency. This is there's 10 megahertz, which is a nice round number. And a lot of stuff, a lot of interesting things from Earth, a lot of things from Jupiter that like in background, Saturn, Uranus, and if we get ambitious, somewhere out there way down in the Jansky level, radio exoplanets are emitting noise. Personally, that's hard to do. We need lots of antennas, or we need to take a telescope and move it closer. That's Breakthrough Starshot, which is kind of a fun thing to think about. So there's a lot of stuff there. The opportunity is great. The opportunity for more interference between, say, galactic background, the sun, with everything else. The noise problem is huge. So this is an attempt to show the noise as experienced by just one dipole. And there's Jupiter, that's not so hot. All the others are even lower. So anything we do out there, we have to say, can we do anything with this noise? And I think we probably can. Things like electrostatically shielded antennas will help. Things like multiple antennas where we average those signals will help. Things like multiple antennas where we exploit the phase difference and actually choose the direction we look. Helps a lot. So, indeed, most people who look at Jupiter use 2 dipoles, not 1. But still, there's a lot we can see. So, we know about the science, we know what the signals might be, we know something about the noise. And do we have an opportunity? Well, it's kind of expensive. What height do we have to go up? In kilometers, we've got to get above maybe 400 kilometers, something like that. At night, we can go lower. And there's a lot going on in the ionosphere. We're up there, we can look at the Earth noise that creeps through, especially at night, and actually understand some things about the ionosphere, correlate that to ground molecules. So many things to look at, but it may be expensive. And obviously people are looking at this, they're saying, let's put up some satellites. And these are indeed the solution. The solution is satellites that will go above the ionosphere filter and give us some new data, give us a new perspective, let us do our own experiments. So these small satellites, lots of designs, thumbsats, nanosats, CubeSats. I'm gonna really interfere with sleeping here. I think I'll pass things around. Do that. I'll start here. So this is Wayne and Colin, or his brother, printing this up at your shop. I think it's a pretty cool little thing. I've got one. Let's see. It's back there on the floor. Anybody want to hold it up? Back there in the corner. And it's, I thought I was going to bring it here, but it's still back there. Yeah, that's good. Just hold it. Don't pick it up with 2 hands or it goes crack. Yeah. Basically, it's just multiple parts. And this is laser cut and 3D printed. It gives you an idea of what it might look like. And this one has a neck on it. So you see the funny neck there. The neck was a solution to this terrible problem with antennas. I've got a bias, and it's borne out by our experiments. That loop antennas are better. So we can build these things. We have challenges. Sometimes they fall apart in testing, stuff like that. But launch rate is already pretty high, 100 a year. Launch rate, amateurs is small. What's actually in there, power supply. This is kind of predicated on the desire to maybe couple into expertise by others. AMSAT in particular. So I not only wore my AMSAT shirt, but I've shown a picture of a cutaway of the Fox satellites and showing the pop-in boards that they use for the data stream through the stacked connectors, the NICADs. They use NICADs because they have certain reliability solutions, no issues. They have some advantages. And in this particular one, which is the AMSAT design, they dedicated a couple of boards to the transceiving bands used by amateurs. And by relaying data that had been stored. So there are opportunities for telemetry back to Earth using this design. Do we build it? They might help us build it. Do we build it also? What do we look at in addition to VLF? Well, we can study what happens with solar emissions. And the coronal mass ejections are very interesting to us. They can cause us great distress. We'll go into it if you wish, but it's something we have to not only learn about because of science, but for survival. We can study coupling of the solar wind to Earth as the magnetic field of the sun goes through its 22-year cycle, and how that stimulates rainfall in different places. There's some data, some interesting results on that. We can study light sail. This is a little far-fetched because most people realize doing light sail research from low Earth orbit. You don't have to stay there, but if you look into it, it's different. There's a lot of drag. But I have pretty sure we can spin up the satellite, spin it down by photon pressure. So, and that's just a very interesting thing to look into. There's also Breakthrough Starshot. It's a very well-funded program driving interstellar physics research, interstellar astronomy, and they're not getting off to a good start. It's well-funded, but they've only been doing this for 15 months. It's only beneficial 15 months. So if we can help them with laser targeting, it's a real plus for them. There's some experiments on solar sails and spin up. And beacons is a bad word, but if we can turn on and off a beacon for various regions, it's a good thing. If we can do ionospheric studies, helping other people that want to do those studies, that's a good thing. Lots of possibilities. Okay. How much time do we have?
Let's say 20 minutes.
Great, okay. So this is kind of the hands-on part, implementation of the solution. And I think you want to...
15, sir.
Pardon?
15.
Oh, because it was that willing to say 20. Now you... I've seen it happen on screen. 22. Okay. Let's start this time. So we need to develop an approach, build and test subsystems, acquire flight experience, and do radio astronomy. And I think this is the killer. I think this is why I've seen there's some really wonderful ideas. The things we're talking about here are not original with me. And I've talked with them about those with a lot of you, plus a lot of other people are pushing these ideas, and they're doing really well. But I think it's difficult to get going. It's really hard to get your... we've launched about 9 balloons from the Little Observatory in Tennessee. And these have done crazy things. They measure background nuclear radiation count, and temperature, altitude, done radio triangulation. We've identified position by GPS and applied GPS and amateur radio. APIS. Yeah, it sounds like a bee. Okay, it is APIS. So we've done these things, and we can do some balloon experiments that show the flight experience. Logistics means we identify partners that also have flight experience and can help us build an integrated satellite. And they're launching users. So this is ambitious and just throw it up there to get comments. But it's not unreasonable to say we could launch a series of satellites. Initially, we do just what we've been talking about. But very soon we can also do some things. If we're further out, we've got a lot of radiation damage. We do radiation healing and spectral analysis, planetary studies, FPGA reprogramming. We can also do, it's not unreasonable to start doing phase coordination between 2 or more satellites. Now, that doesn't have to be as complex as high resolution interferometry. It can just be deciding where you look. Avoid the interference, look at what you want to look at. There are just a lot of things to look at. Different satellites, low Earth and high Earth orbit, geosynchronous orbit, going out to the Earth-Sun L1 point, which is a stable point between the Earth and the Sun. You can do a lot there, and it ties in very well with solar monitoring and identification of harmful coronal mass ejections. Going out, working with the space station using other antennas, working with reprogramming the FPGA for multiple reasons. For example, you can change the nature of the mission by reprogramming the FPGA. It's a very, very plausible thing to do. FPGAs are complicated, but we've got them in radios we're playing with already. And then eventually, the Interstellar project where we send a small instrument somewhere else. And I think that radio astronomy software-defined receivers are kind of a frontier because they integrate, they sense the environment, integrate with full computer. So let's kind of get real about this thing. We could do this one soon. We could do these others, say 2024, 2029, 2035, 2067. Okay, what do we do to implement this? We set up a group that can actually look at the various facets, establish goals, partner, do the engineering studies, and then test prototypes. So that's what we've been trying to do. We looked at the configuration that we might do. We call our group TALSAT, but it's just a preliminary for either going ahead. This is a balloon study going ahead for the satellite or working with SARA. And I think you've probably seen this. Wayne uses this AMSAT photo also. It just shows that the satellite is a fine place to have lots of things to worry about. But very educational, very interesting instrument to build. Okay, how would we start? Well, let's choose a loop. Lots of reasons to do that. Do some pre-filtering, get it away from the ground, have a receiver, ADV system, actually do a fast Fourier transform in flight, and deliver that instrumentation to the Earth. Watchdog timer will ensure that when the power transients occur, there's a restart. So this is what we set out to build. And we designed 3 different approaches. We wanted a CPU package. We looked at the Raspberry Pi and DC boards. We did a couple of different ways of doing the digitization. We looked at antennas, receivers, and transmitter design, and how to integrate. The CPU package. This was one. I took it apart took the antenna apart. But what this is a Raspberry Pi computer with an integrated power supply and display, and it has a deployable antenna. Whereas if you watch a CubeSat, that's the reason there was a neck on the little thing there. So if you take off the wire holding this, it makes noises and these pieces of steel go out in all directions. Don't take that off. Does anyone want to hold this and consider it? Sure. So don't take off the wire. But you can look at this thing. And other stuff. The Raspberry Pi computers, there's several different types. Most people just say 3 types. They're driven by an ADV thing, just a sound card. You can buy these things. I just tried this one the other way. This is one that came out of a junk box somewhere. This is really very cool. This one you can buy for $12 if you want a little sound card. That looks rather nice. It actually has optical inputs, if you believe that, and 2 digitization inputs. So this is what we actually thought we could fly if this didn't work. This does work. This is an El Cheapo thing from us. It's an ADV converter. El Cheapo means, I think that was about $5. The difficulty is, all this stuff I'll tell you about our Pis and the digitizer plugging in, it doesn't work well. And it either doesn't work well because USB can't handle a steady stream. And we want to digitize up to 50 kilohertz in cluster. So the clock on the digitizer runs at 96 kilohertz. Anyway, USB is not what we want. So, pretty little thing. Turns out there's a solution. So I'm going to send around an Pi 3. This is the Raspberry Pi 3. It's really cool. goes up to about 1.2 gigahertz, a lot of memory. And this is a flat max. So this thing can work with it and pushing them together with solid wires. And this does the digitization. It doesn't go through the USB. So we solved that problem. And we haven't connected this guy yet. This is a Raspberry Pi Zero. There are a couple of different types here. And that's what we're going to fly, which is a little bit misleading because actually one of our group jumped around and flew the archive. But on this drone. Anyway, we considered this, and to be honest, we're going to defer the dual loop design for a little bit. But we've got to use a single loop design, go through a receiver, use a flat max. And our Pi is going to fly with a zero and then run VLFRX tools. It's a little trouble to get VLFRX tools going, and we never use them. Programs. They run on various computers, but it's a nice set of tools. And we'll do it FFT, directionality, circular polarization analysis. We don't do that. That would use the tools. And then the transmit spectrum. Yep.
So why do you feel you have to do FFT on board?
Well, if we don't do that, we've got to have a steady stream of data coming back. And it just eats up too much power. If we have
not necessarily.
If we do it on a satellite, the satellite's multifunctional. So we don't want to be doing it.
If you can store the FFT output, you can store the raw data.
You can. The FFT is kind of a composite. It's easier to store one photo. Essentially, the bits in an image are going on. I know.
Say that again. I didn't quite hear.
It's easier to store that processed spectral data, the summary, than it is to transmit full bandwidth all the time. It's less.
You should probably mention you're doing averaging.
Hold it, David.
You should probably mention you're doing averaging, so that's why you're doing a data reduction.
Oh yeah, it's the data reduction. Yeah, thank you. So the data are voluminous, the entire spectrum, and it's just a lot of stuff to transmit.
Which means you're throwing away information that you might decide later
And
on.
that's the reason for the turbo, because if you have pulses coming in, you lose that stuff if you do an FFT. So it's a very good point. You do lose information. Anyway, that was our goal, to see if we can, and what we can do there is do a number of things. Study that. And pull up physical information. And, understand it, doing all that with all the raw data. Just a lot of data.
Hey.
So this is a picture of what's going around. And what you see here is the Pi, and that 3B. That above is Pi 0, and that's the teensy. And the teensy, the reason we're doing that, this thing is to use the data up above. The teensy is low current, just as the Pi 0, but you can run the speed up and down. It doesn't have as much background stuff going on. You can run it all the way to 0, where it's running about 50 microamps something. So you have a lot more control with the teensy. Still got a lot of power. It's just harder to get going, so we might use that. We'll come back to this if anybody wants. That's the teensy running up above here, and it's running a processor, FFT, that generates a waterfall display. The waterfall display is up there. So the thing works. Not ready for flying. The little board has a teensy and a power supply there. This is not flown. This is a crazy antenna. It looks like the thing I passed out, but it's a high beam antenna. So it's a dipole, a little steel tape pieces shoot out, and you've got an electrical dipole that you hook into the proper receiver. This is one of the receivers we built 4 or 5 of them. And this is a low impedance receiver, and it's intended to go to a loop. So this is just looking around, seeing how we can do the best sign-ups on something that flies. So we're using the Raspberry Pi. lots of advantages, but we're going to probably eventually end up continuing. So just, we got our own software, we've done a number of experiments, and check out the on benchtop, purely benchtop. Check out several digitizers, like the Flatmax works fairly well. There's some of the data coming in. That is generated with an iPad, and then run into the RPI and analyze. So we've flown several balloons. Haven't said much about antennas, receivers, for transmitting. This shows 3 of our antennas. That's the package that's floating around. That's that's a superset like antenna. It weighs about 4 pounds. It has 300 feet of wire. These are, I don't know if you call them 30-turn or single-turn antennas. This is the first one that was made from the ribbon cable. So we tried several, and it goes all the way from about 4 ounces. This is the stuff I'm using. And the reason I'm handing these out is that if you know better ribbon cable, let me know. That's prettier, heavier. So I made the first one out of the cheap stuff, and it works pretty well. At the moment, it's tied under this configuration. If you make these things and don't tie them down, they're a bit noisy. So we don't want noise. This is the, be careful with this one. This is the best one. And it's made of very lightweight cable, and the cable is held rigidly, and it doesn't flare.
5 minutes.
Oh, okay. So lots of antennas, they work pretty well. And it's ready for this. So this is my friend McConnell's, one of the co-authors, and he's holding this little box over a table, and this is just about 10 on the table. So if you watch carefully, what happens, the little box is similar to the one I passed around. If anything happens, you may not get to see it. Well, in your imagination, this thing deploys in about a second. And it looks pretty scary. So, they played them on the computer, but apparently not here. So, these are another couple of antennas. There's the one you've seen passed around. This is a loop. It's a nice bit, it looks pretty well. Another loop on the table, this is rather large. And in the center is a loop with a ferrite core. And we usually try to characterize these things. If you have too much capacitance, such as you wind it by hand, or like the rest of it, the thing will be self-resonant. And it's a problem, like the self-resonant frequency of this one, the one shown, is about 100 kilohertz. So you may have that going down into the region you're currently offering. How about integration, flight testing, receiver, final design? You see one there, these are other receiver designs. We tried several. They all work fairly well. I haven't seen many problems with those designs. Transmitter is complete. Typical board weight is about 1 ounce. Same for the transmitter. I think we're okay on the weight. The integration is not complete. We've got to do TTL logic. It looks like it's going to go okay, and eventually we're going to pursue both flight tests. So I think the next thing we might do, I've heard this once before, once already, is have a special interest group here. So we'll discuss that. I'm going to stop. I'm going to see if we've got any.
Yeah, we have a few minutes for questions.
Yeah, if Nick or Wayne, or we want to make comments, please.
What science can you do from a balloon? I think that would be.
From the balloon. What a lot of people are doing is look at the And we just want to look at the variation of background radiation from altitude. And it goes up dramatically. So we have a little GM to Geiger multitude from electronic gold mine. And so we were watching that. That was kind of good. That was interesting. You could do the obvious things with exploding kit. What are the batteries would be gold? In general, what we found is we have 5 crystals or so going for the computer, for clock. They're going to get cold, so we've got to do better temperature control. So we're preparing ourselves to do more interesting things. To some people, it would be an experiment to see if you can look at the variation of temperature with altitude. And if that's what it's going to do. We have done radiation challenge experiments where we had up to 400 people doing triangulation to find the height of our package to see if it agreed with what we measured from pressure. And that was interesting because we got a good read. That one went over 100,000 feet. Most of them have to do that if we don't load them too much. If we load them too much, they start out large. Other science, we plan science from our next launch to see how the noise falls off, because a lot of the noise on these on the VLF and what we're doing with VLF and LF may be going up to the 510 megahertz eventually. But a lot of this noise is near field. It's near field electrical noise that will fall off like 1 over our cube. Near field magnetic will fall off like 1 over our square. So you get away from that. And then in the far field, it's really in the EM waves. It's pretty good. So we can avoid the noise. And that's one advantage of using loops as we go out in orbit. Some of this noise is photoelectronic stuff. And I think some of that's local. We can find out more about that.
Hey,
yeah.
I got a couple of comments around here. Richard passed around this ribbon cable, which is made out of plastic. You're talking about putting it in space.
Yeah.
Does anybody know if the plasticizers that make it plastic may evaporate in a vacuum? What they'll do with the UV light levels and stuff like that? I mean, I noticed like Wayne showed that there was a high failure rate on satellites that went up there, and how much of it was because what stuff was put in a vacuum and it failed from being in a
My
vacuum?
answer to that was,
Do you have a vacuum chamber to test? That could
Oh, I don't.
save you a lot of grief.
We haven't done yet. My feeling is that once it's deployed, as it slowly erodes, it's probably going to be held together by dust a little bit. So it's probably going to work. I'm far more worried that it's going to be stiff from the cold. It's not going to deploy at all. So anything we send out has to be well tested.
Well, it'll be stiff from being cold.
Oh, eternal.
The vacuum will pull some plasticizers out to make it more brittle. UV will make it more brittle.
We're not going to use it. We're not going to use it. We're going to use those beautiful antennas that link them out. Whatever they might be. Maybe. I don't know. I've seen other designs where
I was wondering, if you had a place where you could do the testing, see if stuff holds up in a vacuum, see if it holds up in UV, you could avoid some of the failures that happened to the 14 satellites or whatever that fell apart before they ever got launched. I mean,
I've got a couple of vacuum chambers and a pump, but it's not a high vacuum. We could do testing that would look at the volatility of that.
Okay.
Is anybody interested in interstellar workshop in October in Huntsville? There's some of these outside of the table.
Hey, Dennis Farr, our next speaker. Okay. Sorry about the USB. Spectrum analyzer and sweep generator on a budget. I'm definitely interested.
Budget's always good.
Yeah.
Is this yours?
Yeah, just push the soft.
Are you writing something on it? All right, fine, whatever you say. No problem. Probably you.
say about the
I guess what he's doing is like kind of crossing it somehow to.
You just offset it.
Offset it one to make a loop.
Yeah.
Yeah. Oh yeah, I see. So you shifted the connector just one.
Okay, well, no mind.
It's kind of cool.
It appeared there right before OS. It's there. All right. Hello, my name is Dennis, and I'm a radio astronomer. Does it mean anything? Yeah, it does mean something to some people. Okay, very good. Well, what you're seeing is what happens when there's not enough really to fill up all the time slots. That's okay. I'm okay with that. But I come bearing gifts, so I think maybe I got selected for part of that reason too. My stuff is very simplistic. I started in this about a year ago, and my background has been as a technician, building amplifiers, things like that. So I wanted to build my own LNA at 14.2 and 14.20. So I did that, and then I wanted to be able to test it and see what it was really doing. So I started looking around for simple stuff. Well, actually, what I got into radio astronomy with was those silly little RTL SDR dongles. I thought, you know, if I can do this for 20 bucks, I'm going to be a happy guy. So I got into that. So I'm playing around with that, and I'm trying to find software to use with it. And I came up with 4 different pieces of software that work more or less to various extents. And I wanted to share my experience with those things. So the actual paper looks like this. I don't have it in a PowerPoint, but anyway. So there's a picture of the RTL SDR tied to a signal generator, and that's the other half of my talk, okay, about the signal generator. So as I got started, I put up 1420 and using what's it called, SDR Sharp, and you know, this is a display you get from that. And, you know, obviously it gives you a peek and shows you where it is. And from this I figured out that the RTL SDR gives about 30 to 35 dB a gain based on what you're putting on the input and based on what's shown on the output. So that's kind of a base reference. The problem with this is it doesn't store anything. So, you know, you have to store it here, and my memory is very volatile, so that doesn't work out very well. By the way, I thought I was coming here and going to be part of the comic relief, and then I met Ken Redcat. So that's over. All right, so this was the amplifier chain I built here. Okay, it uses mini circuits. I use 3. They're rated at can't remember what they're rated at, but anyway, and then there's also a filter here. So I ran my signal generator in 1 frequency at a time, plotted the output, put it into Excel, and then came out with this plot here. All right, so that gave me some idea of the bandwidth and the overall gain of my simple little LNA that I built. And then I used it here. It's not easy to see. Hopefully it's more clear in the proceedings. This is the exact same paper. But it, again, using the built-in step function of the signal generator I'm using. So It's pretty simple, but yet it gives you an idea if you're building little cheap amplifiers and just want to know what they do. So, now this was a plot that I had done. The last place I worked was a very high-tech place, had lots of Agilent equipment. So I called the guy up and said, hey, can you sneak this in your pocket and, test my little amplifier chain? Yeah, come on, bring it in, I'll take care of it for you. So this was a plot done on an Agilent high-end sweep generator and spectrum analyzer. So that compares fairly interesting with the one I did with my little stuff, okay? So at least I've got an idea and it gives me something to go on. So then, now I got involved with a school in a STEM program, STEM, your call, down in Lake Wales, Florida. And the instructor there had come to a presentation I did at our local astronomy club on radio astronomy. He said, oh boy, you know, that looks interesting, we want to get into that. Can we do that at our school? I said, sure. Piece of cake, nothing to it. Just buy yourself a little RTL-SDR dongle. But of course the main thing was they had to find a dish. So they did. They found a 10-foot dish, it's been installed. They're buying the ancillary equipment for it now. I'm going to go down there when they get it all set up, hopefully when it cools off a little bit. And we're going to see if we can get their STEM program to understand, you know, the physics of drift scanning. Hopefully we can get a blip on the Milky Way. I mean, that's all I'm hoping. If we get some kind of a blip on the Milky Way with an RTL-SDR dongle, it's a successful program for that STEM program. So that's where we're going with that. But this is another piece of software that I got called RTL-SDR Scanner. It's written in Python, so it can be run on many different platforms. And it gives a pretty good trace. I'm impressed, and it stores, and you can get lots of different readouts of the actual data. Now, here's the cutest little thing in the world. You know, the old saying, it used to be there's an app for that. Well, guess what? There's a spectrum analyzer. This was taken directly off of this device. There's the RTL-SDR, feeds in with a cable, the software is built in, and it's running at 1420. So, can that be an inexpensive radio for doing backyard work? I don't know. I'm going to find out. But it certainly is pretty good for doing outputs from amplifiers and things like that. By the way,
do you know what the app is called?
I'm sorry?
Do you know what the app is called?
If it's in here, if it's not, I'll find it. It may be, I don't know what it's called. I can't believe I didn't put that in there. Okay, I'll make sure I get it.
If you look at your phone.
SDR?
Pardon me?
Was that cubic SDR?
No.
No, cubic, I don't know if I have that in here. I did test that. It's on the screen of my laptop, but that's not, here's cubic right here. Here's cubic right here, but that runs on a laptop, not on, that's not an app, okay?
But if you look on your phone, it will tell you the name of the app.
You're right. Hopefully it's got enough charge. Hopefully it's got enough charge later, I can turn that on. You know, when I came here, I read all the stuff, everything, you know, I got scared to death. Do not bring electronic cameras. Do not bring cell phones. Man, I thought, man, I got taken, you know. Next time I understand what it is I need to be. Okay. All right. So there's the Android app. By the way, I did a test to try to figure out how accurate the actual frequency on these things are. And I thought, okay, well, you know, I'll just tune into my local FM radio station. Well, you know, it goes back and forth. You can't get a frequency. But I live near an airport. So I looked up the tower frequency for the airport, put my little antenna on the front of my RTL-SDR. Tower frequency is 119.5. Spain, got some transmissions, and it is .0000. So I'm very impressed with the frequency accuracy at 119.5. So that was pretty good. Now the next part of the show is about the signal generator. Now I want to bring up a little video and show you. Hopefully this is all going to work. It works in my room. All right, is there sound on this? Do we know if this generates sound?
We heard earlier.
Pardon me?
We did hear it earlier.
Okay, right, there you go, made it all work. All right.
Yeah.
We'll find out in a minute.
Okay, so here I have a network analyzer that I purchased about 10 years ago for about $8,000. And what I have here is a 2.442 gigahertz, a 2.442 gigahertz bandpass filter, 3-pole ceramic filter, and basically I've just put a 50 ohm load on it, and we're measuring the return loss on this guy right now. Now, let's keep in mind that it is at minus 18 dB return loss at 2.442. I want to show you that I'm going to get the same measurement using the TPI 1001B. Also, what I'd like to do is measure the insertion loss of this device.
That's a filter?
Yeah, filter.
Okay, I did not calibrate this cable out. There's probably, gosh, less than 0.3 dB. So I would say the insertion loss is closer to 1.5 dB. But you can see the pass band, and it looks pretty good. It's flat. And so now we're going to do the same measurements with the TPI 1001B.
Just as good as the 10,000.
So I can just send the tape.
Yeah, that's fine.
Speed this up a little bit.
Go to the Analyzer tab. Once again, I'm at 2.442 gigahertz or 2,442 megahertz. The strain is 300, and I'm going to set the generator to 0 dBm because basically I want to see what the insertion loss is. It doesn't make any difference what this frequency is because now the analyzer tab controls the frequency. And if I hit start, we'll basically see the same response. I can put my cursor in here and we got about a dB of loss here. So we're within a half dB of what the $8,000 unit says. And there you go. I mean, if I take this out to 600 and start. Oh, never start. We can see what our rejection is at certain frequencies in the market. We can go to and say, I want my 3 points. We can change the colors. This is memory.
Yeah.
There's a lot that can be done with this. So this is the forward motion, the forward vote. Now I want to show you this question. Of course, all block it would be lost, that's all right. We should have already caught it. If we didn't, but we would have. Now, there's a different way to set it up for reflecting.
Okay, I'm gonna get out of that. You get the idea.
Okay, so to set this up for reflected, I'm going to
Not what I want to show. All right, so anyway, when I contacted the vendor, I bought a similar one on eBay, except it didn't have as many features. When I contacted the vendor and said, you know, because he was discontinuing the old model, and I thought, oh, well, you know, I want to give a talk on it, and I just wonder if the new model, what the features are of it. And so he told me, and it's considerably more than the one I originally used. And he says, oh, you're going to a conference, well, why don't I give you one as a door prize? So it is now a door prize. So, as a technician, on budget, that's $400. The one I have is $250, something like that. It does a lot of nice work. Any questions? Thank you all very much.
I do have one question. Is that thing, that device run with an Android app on anything Android, or?
Yeah, it's an Android app. No, not the generator, but the one I was showing before.
Ah, okay.
Yeah, this one here. Yeah, it's an Android app.
But the single generator runs on.
No, that runs on a PC with a USB interface, and it has internal memory. If you want to have it do something repetitive or send out some signal, you can load the program in it and then disconnect it. As long as you have a 5-volt USB source connected to it, it'll run standalone. It does not have to be tied to the PC. I don't work for this guy, by the way. I just think it's a great product, and he gave it to us, and so hopefully somebody gets to enjoy it.
So that's the RTL SDR?
Yes, that's it right there. That's okay. $20.
Now that only works with Android or iPhone?
No, it works with anything. Laptop. You know, most of the stuff I showed you there was with laptops.
It does not work with an iPhone.
Oh, it does not work with an iPhone?
Okay. It does, what?
It does not work with an iPhone.
No, there's no apps for iPhone.
Okay.
And I just happened to run across this one for Android. Okay. In full disclosure, I put up a 10-foot dish, got my LNA on it, checked everything out. I have yet to get a blip at 1420, but every time I go up there, something else is wrong. The PC won't boot. My power supply is bad. The solder joints come off, and I didn't have a soldering iron. One of these days, everything will come together. So I'm very hopeful that at least someday I'll get a blip at 1420 on the Milky Way or with Cygnus A with this.
They do work. I've got to test that.
What's that?
They do work. I've got to.
Great. That's the best news I've heard all day. Thank you very much. That's worth the whole trip to come up here.
That'll keep you going.
Thank you, Dennis. Yeah. You're proud.
Okay.
Long-term SARA member, right?
Yeah.
17 years. 17
So
years.
Android has that's essentially a USB, right?
Yeah, you need a cable to convert it to a USB.
Okay.
One of those cables. And the only thing that you need is the temperature compensated oscillators in, which is what you want. Drain the battery like crazy. Because they're trying to maintain that crystal that takes power. So some tablets that won't work with because it drains it just says that on power.
Okay.
So you got to get a tablet
Oh, there.
that has sufficient power its battery. All you get-
Or maybe you could add a auxiliary battery pack.
There's a cable that's made that plugs in, has the USB for the device and
power.
and power, which is the way but that's one more than a kit.
Yeah. What do you call that cable?
On the go.
On the go.
That's good. Hi. This shouldn't take all that long. And this is Jim, the co-presenter of Thick Flag, and he should be out there somewhere watching from Hawaii. The DVRR antenna that showed up in a December issue of Sky and Telescope has been a nasty thing that has reared its head every couple of years for the Radio Joe program. Radio Joe, of course, for those of you, I'm sure most of you are familiar with it, but Radio Joe gets us into the educational media platform. And it's an introduction to radio astronomy. This is the article that showed up in Sky and Telescope in 1989, December issue. And it was one page, and that's right here. And this is the antenna right here that has been a thorn in our side. And that's a blow off of the picture. It is basically a 21-inch diameter loop made out of 66 inches of wire placed over a screen, and the wire is a foot above the screen. And according to the instructions in the article, the coax is soldered directly to the wire, the center, and the shield is connected directly to the screen. And then you are to tilt this thing so that the face is pointed at Jupiter. Well, it seems simple enough. This thing was the DVRR, direct-driven ring radiator. It's known to ham radio people. This was originally developed in the 1950s, and those are different versions of the ring radiator. Each one of these is a different size, and you're down to the little tiny one that's right here. It was developed for the military, I believe is the case. It was Northrop. Now, the Radio Jove dipoles, the phase dipoles that we use, require, and if we set up a pair out behind the dorm tonight, you'll see that it does take up some space. It takes up a 25 by 30, something like that, 30 by 45 in order to get this thing up and guide and what have you. So it does take up a little space. And the problem that the Radio Joe program has encountered over the years is that people will want to get involved with Radio Joe, but they don't have the space to put that antenna up. And so as a result, they sort of dig into the internet and they find that 1989 article or some variant of, I need to interrupt, or some variant of that antenna. And why not? The thing is only 2 feet square. And it is very appealing to those people who have limited space to put up an antenna system. I mean, it's an immediate draw. It doesn't take much to put it together. You can build it out of scraps laying around the house. Well, if you do a search on the internet, you can find all kinds of versions of this. This is one holding up the antenna. It is actually built. The actual wire is up here, right in this plastic circle, and they're using this plastic table as the support arms for the whole thing. You look in the paper, it refers to that as the Armstrong rotor. Here's another version that showed up on the internet, and this one actually says Radio Joe on it, which is, you kind of cringe, but you can see that they built this similarly. This is the copper wire right here for the ring. It's
It's on its supports, and they're using a chicken wire behind this as the reflector. And again, using the Armstrong rotor, they're pointing this thing at Jupiter. And I want you to keep that in mind. This one is the one that sort of floored me when I found it. This is the University of Colorado at Boulder, and they actually have this on their website as a lesson plan for middle and high school grades. And they call it the Jovian basketball hoop. But that's on the web as a lesson plan. Well, again, about a year and a half ago, it reared its head again. Somebody came to the Radio Joe group and said, I'd like to, the limited space antenna, I'm going to put this up. And up until this point, we could only say, we don't really think that this is going to work. So finally, Dick and I finally said, enough is enough. We're going to actually build this thing and run tests to document what it does. So what we did was, I built it, put it in my backyard, and all I can say is thank goodness, because when I get home, it's going into the fire. I've been mowing around this thing for a year and a half. We set it up, went all through this current past iteration of Jupiter season. Even though the sun was quiet, we were fortunate enough to catch some solar bursts with it, or during its evaluation. And the last thing we did was we actually attached the EDR to an SDR1 software-defined radio and connected that to Jim Sky's spectrograph software to see whether or not it could even be used as a spectrographic antenna. Well, there's the little bugger that I built. And this picture right here is actually after a year in my yard. It is tilted correctly, as you can see here. It's been aimed so that the angle is correct. And I just literally threw that thing together with scrap I had laying around. I had to anchor it on the ground with these rocks so it wouldn't move. But you can see the wire here. Here's my loop right here. It's on arms. I'm using the same chicken wire that was in the original article. I endeavored to make this as close to that article as I could make it. Physically, everything is measurement-wise exactly the way that article was done. I made a single change, which is that little box right there. I brought the main wire and a ground wire up from the screen into that box so I could put a BNC connector there. Because we were going to make measurements and I had to have something I could connect meters to. So that's the only difference between the magazine and what I constructed, because I needed that little box there so I could have a BNC connector on it. This was connected back to my control room with a run of RG8X coax, which I lab measured at 1.1 dB loss. So there was virtually no loss between it and the receiver. I took an ICOM R75 receiver and went through a rather lengthy process to get it adjusted to maximum dynamic range so that we had the receiver the best it was going to get, and we had as little coax loss as possible, because we wanted, since we were going to make a side-by-side comparison of that with the Jove dipoles, I needed to get that as close to the Jove dipoles as I could, so that there was no, there was no separation. We were doing literally a side-by-side test.
What type of coax do they recommend connecting?
I'm sorry?
What type of coax do they recommend connecting it to?
They didn't make any comments one way or the other. Ooh. So they just said hook coax to it. Oh, read the article. It's so vague. It's so funny.
93.
Yeah, whatever you guess.
Well,
lamp cord.
We needed to literally make some real measurements. So I took my NFJ machine out there. Unfortunately, that's why I put the BNC connector on there. So I could hook that thing up to the antenna and make some real world measurements. And that is the run of measurements that I made from 19 to 22 megahertz. And you can clearly see that this number is all zero, and the SWR measured in greater than 25 to 1. So the first thing we decided was it was really bad. So this is a plot of the fact that that thing is so bad, so lossy, that essentially what this chart shows you is that if I start with 1 dB of loss, which is what I measured, and I measure this up to the maximum of 25 to 1, worse than 25 to 1. And this chart thing doesn't go high enough for 25 to 1. But we took it up to 20 to 1. And if you come over here, that number 4 means that's the added loss to the coax. So we're now up to 5.1 dB of loss in the coax to the receiver without anything intervening between the antenna and the receiver. So you're losing a ton before it even gets there.
That's not a DDR antenna. But that's not a DDR antenna.
That's the DDR.
Not at that frequency.
The DDR that we're evaluating the one that's in Sky and Telescope. I'm not saying anything about any other DDR antenna. Just the one that's in Sky and Telescope. And that's the one that keeps rearing its head and giving us issues.
It's a long history of it. It started back in the 60s. Some group put it together.
Right.
And then Jeff Lichman picked it up and he carried it for a while. And then the other guy in Florida carried it for a while.
Yes.
And then Sickles, thank you.
Yes.
And then for the common impact into Jupiter, I had it, I tried it, I tuned it so I got a good SWR, but I wasn't 66 inches.
Yeah.
I was
well,
a quarter wave.
If you're going to do a quarter wave, this ends up being an almost 6-foot radius or 6-foot diameter for one at 21 megahertz.
What you have pictured is a 2-meter DDR.
Well, yeah, let me get through here. So the first thing we needed to do, since the SWR was hideous, is we had to make a matching network. And again, none of these articles or none of these papers ever said anything about a matching network for this, but we built one. And you can see we dropped the SWR down pretty low. Turns out that even though this thing is advertised as a 21 megahertz, that is not where it was the best SWR. The best SWR was right here at 19.5. But you can see that it's a very, very narrow band, even for what it is. So this is the 2 receivers that we used for the test. The Jove dipoles were connected to my Jove 2 receiver. The DDR-R was connected to the ICOM R75. And again, the R75 was tuned to maximum dynamic range. And that took quite a while to get that set up. That's a whole other paper. So here we're looking at the far field plots. And thank you, Bruce, for doing the DDR-R for us. This is a typical Jove dipole, and this is the main lobe. And if you have it phased for Jupiter, this is the main lobe, and it's pointing at Jupiter. Jupiter would be up here. So right now, for the current iteration, Jupiter is plus or minus about 50 degrees above the horizon. So you can see that that's where the best gain for that antenna is. So that's the whole purpose of having a phased dipole, is that you get payment through cabling to Jupiter. Now this over here is canted that way because it's to match the slope here. And here's the kicker. This is pointing at Jupiter. Now you see the problem. Now you see the issue. If that's pointing at Jupiter, what's this number? That thing's got a deep null in the direction of Jupiter. I mean, it's a hideous null.
So it would receive a lot better if you left it flat.
Yeah.
Exactly. Exactly. This thing has a double lobe. There and there. So if I'm looking at the sky, I've got a lobe there and a lobe there. I don't have one in the center. And this is a 3-dimensional plot of the same thing. And there's the null, right in the center.
You don't catch anything in the hole.
Here is a solar event that we caught with the DDR-R, and this is the Jove trace right here. And this is the beam pattern for the Jove dipoles. And you can see the sun is right in the beam, real nice. We got a beautiful solar burst here. At the same time, this is what we got with the DDR-R, that little picky bump right there. And it was 0.7 dB rise above galactic background. But here's the double lobe thing. The lobe is to the left and to the right. Where's the sun? It's right smack in the middle of that null. So again, you can see this is a bigger view of it, but this was that huge solar burst that the radio Joe dipole saw. It speaks for itself. Here's another one. Now this one is kind of interesting because here again, and there's an explanation for both of these. Here's another solar burst for the Joe. And this one had a 13 dB rise above the background. Now here's the Joe dipoles, and that's where the Joe, it's aimed. And the sun at that time was over here, which means that we would expect less of a signal from the Joe dipoles, which is what we saw. The DDRR actually saw it. You can see this little bump peak here, or this little bump peak here, and then, so it kind of, I mean, it looks like that, only much smaller. But where is the sun? Right on the lobe. So the only time that this thing saw any solar was when the sun was sitting on a lobe, not dead center. There's a blow up of that thing. And again, we saw the sun because it was sitting on the lobe. And by the way, these are our best guess estimates of where those lobes are. That's about where they're at. And by the way, in the paper that I submitted for the proceedings, be careful of what you're reading down here on the bottom, because we were in the last minute to get this paper sent, because we kept hoping we'd get more solar for this presentation. So I didn't have the time to clean up these images, which I cleaned up for this presentation. So I'm going to beg your forgiveness that I got this up here finally, and this down here says red, Joe, blue, DDRR. So I'm going to beg forgiveness for that because I didn't get a chance. Now, this was a general galactic background. We took this on the 19th of July. Please note the scale differences. Here, this is 0 to 200 kilokelvin. This is 0 to 16 kilokelvin. The general background for the Joe dipoles, when I took that, was 80 kilokelvin. We processed this chart. Both these charts were processed the same. We took a bin of 10 and searched for the lowest point. That removed any lightning spikes because this was done in July during the solar, summer, we get lightning storms. So in order to drop out all the lightning interference, I did a bin of 10 looking for the lowest point, and then I did a bin of 10 averaging. So that gave us a nice flat. Did the same with the DDRR. And here's the galactic background with it, 3.39 kilokelvin. Same processing on both of them. With the galactic hump, on the galactic center, Sagittarius passed through. And you can see it, we got a real nice hump right there. Again, that was on the 19th of July, processed exactly the same. Galactic background maximum to minimum, about 2.2 dB, which is exactly what we'd expect to see. And other than this is RF interference, but there's nothing. There's no detectable hump there at all. This was a Jupiter IOB storm on March 27th. And if you look very carefully, that's where Jupiter was sitting in the IOB zone. Again, we've got Jupiter in the dipole beam pattern, and we actually have Jupiter in one of the lobes. Ironically enough, we got it in both. Here are S-bursts, and those things, 8 dB above the background, those are really hot bursts. Over here, nothing. Absolutely nothing. No Jupiter whatsoever. And that's with it in the lobe. We then hooked it to an SDR plate 1. We have their multi-port add-ons. Drawing a blank. What do we call those? Multi-couplers. Yes, thank you. We've got multi-couplers on all the antennas so we can pull multiple receivers off of a single antenna. So I ran the DDRR, And I have another SDR play. This is an SDR play 2, that's an SDR play 1. Kind of both hooked up to the same antenna. There's non-ILA emission, nothing. And the SDR play has an incredible amount of front-end gain plus its FFT. It's got fast Fourier transformation. It'll pull stuff out of the mud like you wouldn't believe. Nothing, absolutely nothing. So, we came to the conclusion that at the same time the DDR yielded galactic background temperature of less than 3 kilokelvin. We interpreted this as the DDR is terribly inefficient. It's providing almost no signal whatsoever from the antenna to the receiver. The DDR has a null on the axis. Where all these people were pointing this thing, they were pointing the worst part of the antenna at the object they were trying to see. Had they turned it this way, they might have stood a ghost of a chance, but holding it this way, there was no way this thing was going to ever work. The rest of the numbers are pretty well self-explanatory. We get a solar burst 24 dB above galactic background, and the only thing we could find on the DDR was a 0.7 dB rise against the galactic background. And this is the point of the whole talk. This thing keeps perpetuating itself. We can't kill it. It's like a bad virus.
But nothing dies on the internet.
Nothing dies. This thing keeps rearing its ugly head, which is why we finally decided to do a quantitative study of this antenna so that we can get it published on the SARA website, the Jove website, and the SUG website, so that when somebody asks about this, we can point to them and say, here's a quantitative analysis of this antenna versus the Jove phase dipole set. If you want to go with this, go ahead, but we're going to tell you right now, it's not worth your time. And again, the examples that I pointed out during the talk, the group from UK, the lady holding the plastic Parsons table up, the guy, the simple decametric, that's the guy that had the one built, had Radio Joe written on it. And the one that continues to just baffle me is the University of Colorado, having it up on their website as a lesson plan. And not one single instance can we find where anybody did any analysis, nobody did any measurements, they just Googled it. Nobody ever tried to see what it was actually physically like.
So did any of those groups ever say a rook?
There's never any comment that they saw anything. They just built it, you know, as a fun thing. You can see Jupiter with it. Well, nobody said they saw Jupiter with it. They just built it, put it on their website. And yet it persists. We can't kill it. So I'm asking you guys, if you know anybody that's even remotely trying to build this thing, please tell them not to waste their time. It's pointless.
The real DDR antenna is well documented in the amateur radio.
Correct. But it has to be cut for the right frequency and the whole thing. Yeah, I'm aware of that.
And I'm saying the next step will be to build a real DDR.
Well, I've got so much going on right now. I've been thinking about building a full-scale, correct one for the right frequency and the whole thing. That would require, and I'm not even going to build it until I do an easy neck model to make sure that it's doing what it's supposed to do.
And I suspect it's not a 50 ohm peak point. I would incidentally suggest you get a VNA instead of an antenna.
Yeah, well, if I decide to do that, it's going to be measured to the nth degree before it ever gets put on my property, because I'm not going to waste my time building this thing and just have it sit out there.
Well, I shall look at it, and if it can be built and transported, I'll bring it next year.
The genesis of this was a guy in England sometime in the early 70s.
Right.
Okay, but Sickles picked it up. There was a guy outside of Atlanta who had built one that was at least a quarter wave.
Right.
I took that, he was a photo op. I ended up bringing, I think, the 24 inches off to get the SWR down. But when we modeled it, we found that all of the gain of an open piece of coax.
Yeah, exactly. And for amateur radio use, you notice where the loads were. They're this way, which is what a ham radio operator wants.
It's a top-loaded
this way.
It's a top-loaded vertical.
Yes.
And I remember back in the 50s, people people making those, they made a 160-meter vertical that was 24 inches high with this top loading. So the thing is, it's like taking a vertical antenna and pointing the end at where you want to go. It can't work.
Exactly. Exactly.
Right? It's got to come off the side or something.
So as a ham radio antenna show,
If you mount it
you're
horizontally,
transmitting
it acts
this
like a vertical antenna that is horizontal with the nose straight up.
Right,
Yes.
which is where they've been pointing this crazy thing. They've been pointing to know where they want to talk, and it's just not going to work.
So the gain is still supposed to be real low though, right?
What?
It's still supposed to be like 0 dBi gain or something really compromised compared to the dipole.
Right. So this was our summary. It's unfortunate that this thing keeps creeping into the literature and as a limited space antenna. Real world side-by-side comparisons, which I did over the last year and a half, it's just turned up exactly what we thought it was going to turn up. But we had to have numbers to show people. We'd like to point out that there is some uncertainty regarding a true scale frequency unit. That was not our point. Our point was to test the one-in-sky telescope. That was our only point, to show that it was not useful for looking at Jupiter, because that sky telescope article says, build this to look at Jupiter. That was the point of the article. So we want to stress that the Joe people, we encourage antenna testing and experimentation, but that is not the way to go.
We concur. Well, what would you recommend for a small space antenna that?
We haven't gotten there yet. We haven't found anything that will
Laws
replace
of
a Joe
physics
dipole.
still apply. You can't get gain out of no.
Gain requires physical
A simple dipole is a lot better.
Yeah, exactly. A simple dipole is better than, if you don't have the space, put up a single, you're going to lose gain, obviously, than a phase pair. But that's better than this.
Just a quick comment. There is an electromagnetic theorem that I learned when I was in college in the 70s that relates the volume of an antenna, the bandwidth of the antenna, and the efficiency of the antenna. And there's only one way to prevent that formula from failing, and that is you have to superconduct it. But if you run the metal at room temperature, and it only occupies this volume, then you can predict the bandwidth of the antenna and the efficiency. Well, it turns out that when you do things that are small, when they get much smaller than about a quarter wavelength, it's precipitous.
Oh, yes.
To the point where you're going to end up with like a kilohertz of bandwidth trying to push 90% efficiency or
Well,
even
our
50% efficiency.
Our goal of SARA is to perpetuate the desire to get into radio astronomy. We want people involved in this. So what's going to happen if a teacher uses that as a lesson plan and they get 0 results? They're going to be turned off. They don't want to get involved with this. They have nothing to show for their time and effort. They get all excited. We're going to look at Jupiter, and then they get nothing. And this just kills them dead on the spot.
Well done.
You had mentioned something, I think, last night about a little bit smaller footprint. Was it a folded double dipole?
I'm using a different set of antennas. I'm using a set of Joe dipoles, which is what my receiver was hooked to.
Okay.
And then when I went to the RSD play units, I went to what we call our terminated folded dipoles, which is a polarized set of dipoles north, south, east, west, going through a hybrid ring to give us right and left polarization. I put them both on the right polarization channel and looked at the non-IOV storm that night. So they could both share that antenna.
Okay, and now that is a little bit smaller footprint, right?
No, not
no,
really.
not really.
No. So I put up the dimensions on it. Do you happen to know offhand?
You can get a 24-foot, or Dave. Dave has a 30-foot.
It's a bigger, but the DVR or the TFD is bigger than the Joe dipoles, right?
It's about the same if you do a square.
Oh, okay.
Now the Moxons, people have had success with Moxons. And I've never used one, but those are a little bit more compact. So
Moxon?
People always ask me why I call my place Hawk's Nest Radio Astronomy Observatory, HNRO. This little goomer right here was flying around my place last week. It's a juvenile red-tailed hawk. And he's sitting on the top of the 4x4 post of my TFD antennas. A couple of years ago, I had a full-grown adult sitting on top of my Joe dipole 4x4s, because I have everything built on 4x4s. The row of pine trees in the background behind him are where the hawks nest. So, Hawks Nest Radio Astronomy Observatory. It's named for a reason. There are hawks there. That's the most beautiful. He was back there practicing flying. He would go from the trees to the ground and back up to the trees. He was practicing pouncing on prey. Now, this goomer over here is Dick Flagg. So we want to applaud Dick Flagg for his help with this project, and I thank you for listening. And just remember, don't perpetuate the myth.
For those of you that are interested in a smaller antenna with gain, you might look at the spider web antenna without all the elements. Just put in one element. The spider web antenna at an appropriate distance above the ground will give you a lobe at the elevation angle you want. This is a very, very complex antenna. Students with the whole series. We have told today,
Oh, we get another break.
Somehow
you can bow it
it's not going to work.
Because what I'm doing is I'm taking the output so I have to go. I'm going to take this out. I'm going to trip on the source.
No, bring it.
Well, here's the
Is there do you have power out behind your room to set
I do.
Do an experiment.
Sure, why?
Check it out.
Check what out? Oh, yeah. I'm hoping that this Father Crowley sent down the phone number.
Everybody's got their phone numbers and code.
Okay, good. Here, I'll show you.
All right, well, we'll set up.